Good morning to everybody, and welcome to this international session of the RadMet 2021 conference that I have the pleasure and the honor to open. For this opportunity, I want to thank all the organizing committee and particularly my colleague and friend Andrea Antonini, who is the president of this year's conference, RadMet. I'm Alberto Ortolani. I am a senior researcher at CNR, so the National Research Council of Italy. Namely, I belong to the Institute for the Bioeconomy, former Institute of Biometeorology. I am also the head of the atmospheric division at LaMMA. In fact, LaMMA is a consortium between the regional administration of Tuscany and CNR. And so CNR participates, providing personnel to this consortium, and I am part of this personnel, so part of the researchers and technicians that developed the larger parts of their work at LaMMA. The scope of LaMMA is not only research. This is also, and we could say mainly, the operational service for meteorology in Tuscany. So it provides operational forecasts for the civil protection, and not only for atmosphere, also when we say forecast, we include also air quality and regional oceanography, sea state. So if we have to describe LaMMA just using a few keywords, we could say meteorology, also regional climatology, regional oceanography, and air quality, and also geomatics. So all these subjects are developed not only at regional level, because our interests go also beyond. Just to do an example, LaMMA provides operational forecasts also for the Italian coast guards all over the area of national interest. You can imagine easily that radar meteorology have a key role in these activities. In fact, we have developed a regional network of small radars in X-band that is provide integrated information with the largest networks, for example, and mainly the national radar network, and also the network coming from the cooperation with transboundary projects between Italy and France. LaMMA offices are in 3 places in Tuscany, but we are, transmitting from the main one in Sesto Fiorentino, close to Florence, where we are supposed to have this conference when, 2 years ago, Andrea Antonini proposed, we had a discussion with him, and we proposed to the end of the last RadMet conference, Florence, as the place where to have the next RadMet conference, so the RadMet conference of this year. And at that time, of course, we were thinking about a normal conference, so with people meeting together, physically, and speaking together, shaking hands, and all the normal things that we have always done up to 1 year ago. But of course, the pandemic has deeply changed our way to think the everyday work and more generally the everyday life. Having a huge effect in these, normal things that we were used to do. If we think in a world what has happened, we were asked to, be resilient to this new event. And in fact, we have to rethink the way to do these normal things, and also to rethink the way to do RadMet. And so RadMet 2021 is an example of practical resilience, because we have transformed it from a physical conference to a digital one, a fully digital format that, to be frank, is coming out a very interesting conference with a large participation. In fact, the numbers of participants are even more the one of the previous editions of the conference. This international session is even more than just an example of resilience, because we have transformed a limit coming from a very huge problem in an opportunity. In fact, probably without the pandemic, we would never thought to have this addition of the international session to the normal one because of course, of organizational limits. And so when the organizing committee has this idea, we all thought it could be really a wonderful opportunity. And in fact, I mean, now we are going to start a session where the speakers are top science in the subject of radar meteorology, but also on other related subjects. So from this point of view, I think that it's going to come really a great conference day. I say resilience, and this is a word also contained in the title of this year RadMet conference. In fact, I mean, the RadMet 2021 is named also radar meteorology between science and resilience. And in fact, of course, radar meteorology is thought to be one of the key tool to address the climate change, so especially thinking about the, let's say, increasing number and problems related to the extreme events. And from this point of view, radar meteorology can have a key role to help us to be resilient on these issues. So, I mean, I'm speaking about resilience, but of course it's hard to accept the changes that we can have also about this conference. If we go back thinking to what has happened to some previous conference where some of us, me too, met some of you. I'm thinking about the last event happened in Nara, Japan, in September 2019. It was the AMS, International Conference on Radar Meteorology. And also I'm thinking about the ERAD conference in 2018 at Wageningen in the Netherlands. These were really two amazing conferences. RadMet cannot be compared to these conferences, especially in this international session. But the idea was to gather together a larger community with respect to the national one, not only a European community, but also people, speakers coming from the extreme east with respect to Europe, so from Japan up to the extreme west, so from the USA. So we are very happy to have these top speakers that have accepted to participate to this international session. Our aim is to, not to, say, as I told you before, not to compare this session with the other amazing conferences, but to, let's say, build a bridge between the two ERAD conferences, so the last one and the next one, in order to, let's say, keep alive the use to stay together, exchange ideas, results, research, problems, and also friendship beyond any national boundary. So, I mean, when we all hope to meet together again in the next future, but of course we don't know when it will be really feasible. So in the meantime, what we can do is just to exploit the opportunity that we have and to do what is feasible. And so now we can do it enjoying the today session that I believe will be a very amazing conference day. So I think it's time to let's start with this RadMet 2021 international session. So let's say I hope the best, and let's say thank you to everybody.
Hi, hello to everybody and to all the colleagues connected from around Europe and also, maybe not yet from the US, where it's still night, but from Japan, maybe yes. So hello to everybody, I'm Valentina Grasso and I am a colleague of Alberto, and I'm worked on the organization of the conference, and I just want to give you some advice to smoothly run these day conferences, this international session. So speakers will be introduced by moderators in the different session, and they will have 20 minutes to make their speech and 5 minutes for question and answer. So to stay on time, we thought to give you some advice. So when you have 2 minutes left, you will hear a double ringtone like this. Okay, this means that you have 2 minutes left. Then when you have just 1 minute left, will hear one ringtone like this. Okay, just to help you to follow the timetable and to be on time with the whole session of the morning and the afternoon. Also, please just give sometimes a look at the chat in the Zoom platform, because the RadMed supporting group maybe will send you some personal messages if there is some special need, or a message to everybody to inform everybody without interrupting the conference. So please have a look sometimes. And also to the speakers and to moderators, please turn on your camera just a few minutes before you will be online. You will have the floor to you, so that we can see you smoothly before that you will be sharing your presentation. I'm sure that everybody is already familiar with the Zoom platform, because this is not the first online conference that you will be participating in, I guess. But just to remind you some quick advice, so question will be made using the chat if you want, or also using the raising hand function. So moderators then will give the floor to the people who has raised his hand, and question. Of course, the today language is English, so please try to make your question in English. If you just have trouble making question in English, you can write the question in the chat, also in Italian, if it's better for you, and the moderators will be translating it in English and pose it to the speaker, that will answer, of course, in English. So this is also the same rule for YouTube. I'm saying hello also to the people who have been following us in the YouTube streaming. So today the language will be English. In the YouTube chat, we will try to use both, just to give help to the people who maybe would be not just familiar with it, or jumping in the conference and not really understanding why in the Consorzio LaMMA channel there is an English conference. So just for this. During the coffee break, as in the previous day of the conference, we will have the opportunity to meet two radar companies, ELDES and Euroelettronica ICAS. So if you want to meet the people from the company, we will be opening the room function of Zoom just a few minutes before the coffee break. We will be around 11. So once you see the icon in the bottom bar of your Zoom application, you can enter the room that will be named, of course, as ELDES and Euroelettronica ICAS, and you will find people from the company to have a chat or see some materials. Then you can exit the room and just enter back in the main hall of the conference. I think I said everything, that's all. So I leave the floor to the moderators. For the first session, the moderators are the colleague Frank Marzano, that I see is already there, and Roberto Cremonini. Hi, Roberto and Frank. Good morning. And also we will have...
Good morning, Valentina.
And also we will have Francesca, who is just the LaMMA staff person, who also in the back side of the conference to give help if needed. So, well, let's begin with this international session. Have a good day.
Thank you, Valentina. I welcome all of you. Thanks to Alberto for the nice introduction. So we won't spend any more words about this initiative that we hope it will be useful and interesting, but we are sure about that. Together with my colleague Roberto Cremonini, we will introduce this first session of the conference, an international session of this conference. The first session is about weather radar systems and the networks. The next two sessions will be about radar nowcasting and precipitation retrieval, and the last one in the early afternoon advanced radar systems and tools. So I may introduce the first speaker, who is Tomo Ushio, who is connected, I guess, from Japan. So we really thank Tomo for being here. You know, we know it's a little bit late in Japan, but still, Tomo was so kind to join us, also to give this flavor of internationality. So as we pointed out, we have plenty of time with respect to a normal conference, which is about 25 minutes overall, which we should be including also questions, as Valentina pointed out, with all the rings that she explained. So the title of the presentation of Tomo is about a new technology, which is coming up: phase array radar development and observations. So please, Tomo, and thanks in advance.
Thank you very much. So can I share my slide here?
Yeah, you can share.
But
you should have a arrow pointing up.
okay.
Just in the bottom line of the. Yeah.
Okay.
That's perfect. Yeah, that's perfect, Tomo. Thanks.
Okay. Thank you very much. So I'm very honored to be here with you, particularly under this situation. So today I'd like to talk about our radar system. This is, yes, photography is here. This is the first phased array weather radar system in Japan. Actually, this was installed in my university at the top of building in my university in 2012, like this. Actually, my office is located here at the fourth floor. I'm on a fourth floor. So at the top of my building, so we have this kind of white radome, and inside this radome, as you can see here, phased radar system is installed. So as you can see from this movie, this radar system takes electronic scanning for elevation and mechanical scanning for azimuth. This radar system achieves 3D scanning with 100 elevation angle up to 6 kilometers in just 30 seconds to detect severe storm instantaneously in our area, in Osaka urban area. So as you know very well, usual parabolic type radar system has pencil beam, mechanical scanning both in elevation and azimuth angle. Parabolic antenna goes around in a certain elevation angle like this. On the other hand, the phased radar system we developed transmit wide beam, farm beam like this. After receiving at 128 antenna elements, sharp beam is formed. So with this radar system, we take electrical scanning only in elevation. So this is all 128 antenna elements here, and for each antenna element, we have a down converter and an AD converter, and the power amplifier is connected only to 24 antenna elements. That means we have 10 degree transmit beam width. The scattered signals are received by all 128 antenna elements right here, and then all the signal is down converted and digitized. So we have 128 digitized. So at the signal processing stage, sharp received beams of about 1 degree are formed by digital signal processing. Digital signal processor, DSP. So like this, in such a way, so this is one example of the thunderstorm developed in northern Osaka area in July, almost 10 years ago. Our radar system is located around here, northern part of Osaka. So this is a vertical cross-section in east to west direction. And also, if you look at here, you can see the in north to south vertical cross-section. So since our radar system has 100 elevation angle observation, so detailed image, dense image of thunderstorm can be captured with this radar system. And this kind of images are updated in every 30 seconds. And so you can see the detailed behavior of thunderstorm with this spatial and temporal resolution like this. If you look at the isolated thunderstorm, so you can see more impressive picture animation like this. So you can see, for example, if you look at here, so you can see that descend downward process of the core of the thunderstorm like this. So with 30 second 100 meter resolution for 100 elevation angle over 60 kilometers in radius, our phase array radar observation is very impressive and shows a descending process of the core of a thunderstorm, which is a precursor of the extremely rainfall event. 3 years later, we installed another phase array radar system 60 kilometers away from our university, like this. So after that, we have network, phase array radar network. As long as I know, this is the first phase array radar network all over the world. And also, the same radar system was installed in Tokyo metropolitan area. And after that, we have developed the dual polarimetric phase array radar system in Tokyo metropolitan area 3 years ago. So we started a social experiment using this radar network. The data from phase array radar and also lightning discharge are transferred to the huge data center located in Tokyo, Toshiba, through internet. And there, so we collect not only the phase array radar, but also another radar systems and ground-based sensors collected by Japan meteorological agencies are processed here. And then the processed data also transferred to Osaka local government through internet. And at the Osaka local government, public park or some sections dealing with warning and or warning to the heavy precipitation sees the display, and this data will help them to determine, the people are evacuating or not. So using this network, this is one example of the isolated thunderstorm. So you can see the newly developed core of thunderstorm and also the decaying of the thunderstorm like this. So this is a snapshot. So from here to here, 15 minutes. And 15 minutes ago, a new core was formed at 4 or 5 kilometers in height. And then this core began to descend. And after that, new core was formed again, only a little bit, a few hundred kilometers away from here. So this scenario is very, very important to accurately nowcast or forecast the rainfall rate 10 or 15 minutes later. So in order to make best use of this data set, we have developed three-dimensional nowcasting system like this. So usually, in order to nowcast or forecast the rainfall rate, so people use two-dimensional nowcasting model like this. But however, since we have three-dimensional information from phase array weather radar, so this kind of information is very, very helpful and useful and effective to better nowcast the precipitation rate like this. So this is one of the evaluation. So this is time and this is a rain rate. The black line shows the result from the two-dimensional nowcasting model, and the blue bars are the measurement from rain gauge. So our 3D nowcasting model is much, much better than the conventional two-dimensional nowcasting model. So this is very useful. And also, if you are interested in dual polarimetric observation from phase array weather radar, so this is a ZH, the Doppler velocity, and ZDR, 5dP, KDP, and ROHB like this. And then this is some animation in every 30 seconds. For this polarimetric parameters, and the upper left is reflectivity, and the upper right is Doppler velocity. The lower left is the ZDR actually, and the right bottom is the distribution of ρHD. So this is also very impressive. So in order to evaluate the how accurate the observation is for phase array weather radar, so this is a result of the rainfall estimation compared to the rain gauge on ground. This is the result from the reflectivity only estimation, and the middle is the estimation only from KDP, and the right is the combination with reflectivity and KDP. So as you can see from here, the apparently the rainfall estimation from reflectivity and KDP are superior to those to other estimations. The correlation is surprisingly very high, 0.86 or more, and the root mean square error is 1.59 millimeters per hour. So if you compare with the conventional parabolic type radar system, the right one is a parabolic type radar system estimation from the parabolic type radar estimation, and the left one is dual polarimetric phasor radar system compared to the rain gauge. So as you can see from here, the correlation is a little bit better than the conventional parabolic type radar system, and also root mean square error is better than the parabolic type radar system. So maybe the phasor radar system is totally better than the parabolic type radar system in terms of rainfall rate estimation. So let's go back to the social experiment. So actually in Japan, so as a result of global warming, the torrential localized heavy rainfall tend to occur more frequently than before. For example, this is one example of the event. So in this event, actually this river, the height of the river is suddenly up 1.34 meters just in 10 minutes. And unfortunately, 5 people died in this event. So this is one of the most, important hazardous event in Japan recently. So we need accurate high space and time forecast and coupling with model. So this is a result of our social experiment. In this event, with our radar system, heavy rainfall advisory was issued, and people started to evacuate at 4:09 in the PM in the evening. And after that, 12 minutes later, the rainfall exceeding 50 millimeters per hour started. And also we detected lightning. So on the other hand, actually, the advisory from Japan Meteorological Agencies was right, very, very right. Almost 20 minutes later. So it is too late. So using this phase array radar system, probably we can evacuate more earlier and more and safer. So also we have some activities for data simulations. Yep, we have a very, very strong collaboration with K-Computer. K-Computer is #1 computer system in the world 3 years ago. Very, very huge high-performance computing system. The data from phase array radar system is now transferred to the K-Computer system in real time, actually. And this is one example of the data simulation. As you know, the assimilating precipitation is very, very difficult to weather numerical weather prediction model. So, however, our colleagues did that. So this is observation, and this is simulations with 100 meters resolution. And this is a simulation without any data simulation. So as you can see from here, without phase array radar system, the prediction or forecast is totally different. And the phase array radar system, the data from the phase array radar system is very, very influential and effective to better forecast the rainfall system like this. Okay, very impressive. And also, using the dual polarimetric weather radar system, which was installed in Tokyo metropolitan area 3 years ago, we started some demonstration using the weather radar data and the K-computer system. So this is one example of our result. So you can see some rainfall forecast like this. And actually, using this system, we were planning to demonstrate in Tokyo Olympic Games before the COVID-19 pandemic. But however, it was delayed. So maybe from next week, we will start this kind of demonstration in Tokyo Olympic Games. Okay. So this is a summary of my talk today. So phase array weather radar gives us a detailed behavior of precipitation system with high temporal and spatial resolution, as I showed in the animation particularly. And also rainfall estimation from phase array radar is better than that from the parabolic type radar system, as I showed, with the comparison of rain gauge measurement. And data simulation technique and technologies with big data from phase array weather radar observation will open new field. So I think that's it. Thank you very much.
Thanks a lot, Tomo, for your very nice presentation and also for letting also time for questions. So there are some questions coming up. If there are some questions from Jordi Figueres, or not, Jordi, if you want to switch on your microphone and directly pose the question, as well the same for Gianfranco Vulpiani.
Hello, thank you very much for this presentation. I enjoyed it a lot. It's really impressive, I must say. Just a couple of curiosities about the system. First, what was the minimum and maximum elevation that you used? You said you had 100 elevations, but you did not specify the elevation angles that you are seeing. My second question is about the sensitivity of the system, and I was wondering whether I imagine this uses a modulated signal, whether you have a blind range close to the radar or not.
Okay. For the second question, the sensitivity is 17 dBz at 60 kilometers.
Mm-hmm.
That is the minimum requirement of a radar system. And for first question, can I repeat again?
The minimum and maximum elevations.
Oh, elevation.
That you can get.
Okay, we can scan whole sky actually, zero, parallel to the ground to the 19 degree.
Mm-hmm.
The whole sky.
But you just have a 10 degree fan beam at.
Right, but however, at the receiving stage, we make it narrow at the receiving stage, every 1 degree.
Yeah, so I understand that, but the transmission is 10 degree, no? So you have to do it in several steps. This one.
Yes, 10 degree and gradually wider to the upper angle.
Okay, and the last question, if I may. Do you have a blind range close to the radar?
No, actually, we have two modes for transmitting. One is the short pulse, and another one long pulse for pulse compression.
Okay.
So in such a way, we could mitigate the blind range of the radar system.
And are you happy with the transition between the two modes? Is it okay?
Yeah.
Okay. Thank you very much.
Thanks to you, Jordi. I think the Gianfranco Vulpiani can get the mic. Yeah, please, Gianfranco.
Thank you very much. Very interesting. I have a couple of questions. The first is I would like to know if the radar is ready for the market, or is still a prototype that you use for test for.
Yeah, you can buy.
Okay. Okay.
So it is Toshiba sells you. Toshiba. Do you know Toshiba?
Ah, Toshiba. Okay, understand. Okay. The second. Okay. The second question is related to the scatter plots that you have shown regarding the rainfall estimation. Apparently the RKDP algorithm didn't perform much better than the RZ algorithm for higher rainfall rates. Is more or less the same in terms of dispersion, I mean, so it was quite comparable. And so I was wondering how KDP is estimated and.
Yeah, actually, please look at the horizontal axis. That is from 0 to 25 millimeter per hour. So that is, less than the moderate rainfall rate. So in my scatter plot, the range is limited to 0 to 25 millimeter per hour. So that is, if we expand the 50 millimeters per hour or 60, 70 millimeters per hour, probably the LKDB is superior than the RZ relationship.
Okay.
So, if you have very big rainfall, sometimes the KDP is very, very hard to extract. So that's why you have this kind of impression.
Okay, thank you.
You're muted, Frank.
Yeah, sorry. Thanks, Tomo. I was just wondering if I understood well, you're using pulse compression. Is it correct? Do you have side effects due to the side lobes when using the pulse compression techniques? Do you see some artifacts?
Yes, we have. But however, so now we could succeeded in eliminating this side effect. We make use of pulse shape algorithm using genetic algorithm. So in such a way, maybe range side lobe is less than 60 dBz or 70 dBz, very, very low. So now we have good quality for this.
Yeah, this is actually very important because it's opening the application, the widespread application of the pulse compression.
I agree with you.
Thanks a lot, Tomo, for your kind presentation and also for being here, even though you are so far.
I hope I will be there.
Okay. Yeah. So we can go on and to the next presentation. And next presentation is coming from our friend Remko Uijlenhoet. I don't know, Remko. I always have some doubts about pronouncing your surname, but
it's okay. It's okay, Frank. Thank you very much.
This is one of the most difficult, indeed. So thanks, Remko, for being here. And Remko was one of the pioneers in the application of opportunistic quantitative precipitation estimation using commercial microwave links. And so we are very pleased to host Remko and his presentation about this topic and the state of the art and the latest advances. Please, Remko.
Yeah, thank you very much, Frank, for the kind introduction. And thank you very much for the organizers for inviting me to give this presentation. I will share my screen and see if that works. You should be able to see this.
Yeah, we are seeing it. Yeah, we are in presentation mode. Thanks, Remko.
Let me minimize this. Okay, good morning, everybody, at least in Europe. Good evening for those of you who are in the Far East, such as the previous speaker. And good night for those of you already connected from the Far West. I don't expect you to be here, by the way, but I guess these presentations are also streamed through YouTube, so you will be able to also watch them offline. So what we're going to do today is slightly change gears with respect to the previous presentation. Because we're going to move from dedicated rainfall sensors, such as weather radars, to what we call opportunistic rainfall sensors, namely, in this case, commercial microwave links. Now, before continuing, I would like to acknowledge my collaborators, Aart Overeem and Hidde Lijnse from KNMI, the Royal Netherlands Meteorological Institute, and Arjan Drosten from Wageningen University and Research. And you also see a logo from the GSMA, the GSM Association, with whom we are collaborating closely, as you will see in a minute. So today's presentation will deal with the types of sensors you see here on this slide. The microwave links we know all too much from our cellular communication. And as you can imagine, whenever it rains, the signal between the transmitting antenna and the receiving antenna is being attenuated. And we're going to use that attenuation to estimate rainfall rates. And because we're able to do that for each individual microwave link, we can actually use each of those microwave links as a path average rain gauge. And by combining those, we're able to produce space-time rainfall maps and also short-term forecasts. Now, today's presentation will be mainly geared towards applications, not so much in the Western world, but more in what is called the Global South. Typically, in the Global South, dedicated precipitation measurements, either from rain gauge networks or from weather radars, are really sparse. At the same time, there is a large need for gridded precipitation products in those areas. And in particular, we're thinking of Africa and parts of South and Southeast Asia. And obviously, those precipitation products are required, are needed for a range of applications, notably in weather forecasting and in water management, but also various agricultural applications. And even though in those areas the density of dedicated rainfall sensors is very sparse, at the same time we're witnessing a very rapid growth in the basically the number of cellular connections worldwide, as is shown here on the lower right-hand side of the screen. And that is not only the case in the Western world, but also in the Global South. And what we're doing actually is trying to make use of that development in order to come up with a opportunistic manner to estimate space-time rainfall fields. Now, dedicated sensors, you know all too well. Obviously, the theme of this conference is weather radar. And on the upper left-hand side of the screen, you see the global network of weather radars, which, of course, has a very good coverage in particularly the northern hemisphere. But in the Global South, the coverage is very sparse. The same actually holds for the rain gauge networks that we're operating globally. Again, the same areas, large parts of South America, of Africa, and also parts of South and Southeast Asia lack spatial coverage. Of course, as you can see on the lower right-hand side, we have our satellites, either in low Earth orbit or geostationary, which can provide us with very valuable precipitation information, notably also over the oceans. But of course, these are remote sensing estimates and hence need ground validation and also ground measurements to further improve retrieval algorithms. And that is where the commercial microwave links come in on the upper right-hand side, because what we're seeing is that even in areas where dedicated sensing networks are relatively sparse, people are using cellular communication. And hence a cellular communication infrastructure in the form often of microwave links is existing in those areas. And we're trying to opportunistically, in the good sense of the word that is, take advantage of that existing cellular infrastructure. So basically the solution that we propose is called commercial microwave links, in short, CMLs. And the principle of rainfall estimation using CMLs is based on the fact that rainfall attenuates signals as they are transmitted from one antenna of a telephone tower to another. And the idea is to convert those attenuations, which are stored operationally in the network management systems of mobile network operators, to path average rainfall intensities, and subsequently use open source software that we developed to estimate space-time rainfall maps and to use potentially nowcasting algorithms to perform short-term rainfall forecasts purely based on existing cellular infrastructure. Now, let's start with some examples for the Netherlands, which you can see here on the right-hand side with a network from one particular cellular provider in our country. And we have used the great collaboration we have had with that cellular provider, namely T-Mobile, to develop a open source package in R called RainLink that is freely available online through the link that you can see on the lower side of the screen. And that package consists of a number of steps, namely pre-processing of commercial microwave link data as they are obtained from the network management systems of mobile network operators. It includes a wet-dry classification to distinguish between rainy and dry periods and microwave links. We need to determine a reference level. We're filtering a number of outliers due to different sources of error from the perspective of rainfall estimation, notably wet antennas. And then we estimate rainfall rates, path average rainfall rates on the basis of the filtered attenuations. And finally, we use a geostatistical algorithm to interpolate the path average to obtain spatial rainfall maps, as can be seen here on the right-hand side for the city of Amsterdam in the Netherlands. Now, the basic retrieval principle of microwave links, as I explained before, comes from the fact that rainfall attenuates microwave as they travel through precipitation, and that attenuation can be related to the rainfall rate in the form of a power law, as is shown on the upper right-hand side of this screen, with an exponent that, as you can very clearly see in that graph on the upper right-hand side of the screen, is very close to 1 for microwave frequencies of the order of 30 gigahertz. And by chance, typical frequencies employed by mobile network operators operationally are of the order of 30 gigahertz, let's say between 10 and 40 gigahertz. And that suggests that microwave links from cellular communication networks can actually be used as path average rain gauges because the specific attenuation suffered by the microwave links is nearly proportional to the rainfall rate along the path between transmitter and receiver. And as a result, as you can see on the lower side of this screen, the relationship between rainfall rate and attenuation is expected to be very nearly linear. And also the scatter associated with that, the uncertainty associated with it, is going to be really small compared to a typical weather radar frequency of 10 gigahertz, as is shown on the lower left-hand side of the screen. Now, we can apply this technique to estimate rainfall rates based on the attenuations from one single microwave link. This is an example for the city center of Amsterdam again, where you see in the upper left-hand side of the screen time series of received signal levels with very clear drops whenever it rains, as is indicated by the gray line, which is basically the path average rainfall rate obtained from a gauge-adjusted radar product. Now, using that power law that I explained on the previous slide, which is actually very nearly a linear relationship, we can use those attenuations and convert them to rainfall rates. And that is shown on the lower left-hand side of the screen in terms of rainfall intensities, and in the middle of the screen in terms of rainfall accumulations. Now, obviously, if we can do this for one single microwave link, we can do this for many individual microwave links and use the open source package RainLink, which employs a geostatistical interpolation to obtain space-time rainfall estimates, as can be seen here, with on the right-hand side, the reference product, the best available rainfall product in the Netherlands based on radar, 2 radars and a network of rain gauges. And on the left-hand side, the space-time rainfall fields that can be obtained from using the existing cellular infrastructure alone. And as you can see, the results are really promising. Obviously, there are differences, which is to be expected for a opportunistic sensor, which was not designed to measure rainfall. Now, obviously, this is all very interesting, but in the Netherlands and in many parts of the Western world, we do have, as we have already seen, dense networks of dedicated rainfall centers. So the largest added value, if you will, of this type of opportunistic sensing technique is in those parts of the world with sparse dedicated networks, such as Africa. And together with colleagues from France and Germany and a whole bunch of colleagues from various African countries, we organized a training school a number of years ago in Ouagadougou, Burkina Faso, trying to, first of all, convince mobile network operators to share their data. And secondly, also to basically engage colleagues from meteorological and hydrological services in using those techniques to obtain rainfall fields. And an example for the city of Lagos in Nigeria is shown here on the right-hand side, with on the upper right-hand side, a rainfall system moving over the Lagos area based on basically the GPM iMerge satellite-based product. And on the lower right-hand side, space-time rainfall estimates obtained from the very dense commercial microwave link network over the city of Lagos, Nigeria, one of the largest cities on the African continent, by the way. Now, in collaboration with our partner GSMA, the GSM Association based in London, we're actually thinking of and actually pursuing operational applications of these products in a variety of economic areas, notably weather forecasting, water management, but also, and that is a particular interest of the GSMA, agriculture. You can see a number of examples here, and if you're interested, you can click on the link on the lower end of the screen to find out more about what GSMA is interested in. And the GSM Association has also thought of potential revenues for mobile network operators that could be the starting point of a basically a business case for mobile network operators to entice them to share their data with potential end users in the water management sector, the weather forecasting sector, or the agricultural sector. And here you see for a number of countries in Africa and Asia, estimates of the potential revenues depending on the country coverage in terms of commercial microwave links. Again, these are estimates obtained from our partner, the GSM Association, which can be accessed through the link provided on the lower end of the screen. Now, obviously, I can imagine that most people in the audience here today are not so much interested in the business cases, but more in the science side of things. So for those of you that are interested more in the quantitative precipitation estimates, providing here a comparison between rainfall estimates on the left-hand side based on a commercial microwave link network in Sri Lanka, and on the right-hand side a synchronous rainfall field estimated from GPM, basically from the GPM dual frequency radar. And what you can very clearly see is that in terms of space-time rainfall estimates, there's excellent agreement between the CML-based product and the satellite radar product. And of course, with respect to the satellite-borne radar product, the CML product has the advantage of providing new rainfall estimates every quarter of an hour. And actually, we report about this in a recently accepted paper in Environmental Research Letters. Now, taking a closer look at comparisons between estimates from the microwave links as compared to dedicated sensors, in this case, a rain gauge network. And in this case, we compared the interpolated rainfall fields at those locations where rain gauges are present at the hourly scale. In this particular figure on the left-hand side, you see the corresponding scatter plot showing actually that our microwave estimates are having very little bias, a significant scatter, obviously, but that scatter is actually also expected to be there, given the fact that, of course, these are opportunistic sensors, not dedicated sensors. And at the same time, if you would make a scatter plot of two nearby rain gauges, I'm pretty sure you would see a similar amount of scatter and uncertainty. Now, of course, if we're able to make quantitative precipitation estimates using commercial microwave links, we're also, in principle, able to basically turn those estimates into short-term forecasts called nowcasts. And that is something that we tried last year using data from the Netherlands. What you can clearly see here is on the left-hand side, short-term rainfall forecasts based on commercial microwave links. In the middle, short-term forecasts using exactly the same algorithm, using the unadjusted real-time radar product over the Netherlands. And on the right-hand side, the gauge-adjusted radar reference. And what you can see for this particular event is that actually the short-term forecasts based on the commercial microwave links provide better estimates of the precipitation in the near future than the unadjusted real-time radar product. If you want to know more about this, please consult the paper that is indicated on the lower side of the screen. So, closing off this presentation, what we feel is important right now is to upscale the current knowledge and expertise that we have obtained together with other partners in Germany and in Israel, notably on rainfall monitoring and nowcasting, and really scale this up from individual countries to, let's say, significant parts of continents. Of course, what is important there too is to localize the algorithm, adjust it to the local network properties as well as to the local rainfall climatology, and ultimately in collaboration with mobile network operators develop basically business cases to entice mobile network operators to share their data. And developing such business cases is actually something that we're currently doing in collaboration with, again, GSMA and a number of mobile network operators and private consulting firms. And we very much believe that after about 15 years of scientific research on this particular type of opportunistic rainfall sensing, it is really time to make this happen, and meaning make operational use of commercial microwave link data for space-time rainfall estimation and short-term forecasting a reality. And for that, we need to collaborate, obviously, with GSMA and with mobile network operators. And if you're interested in one particular business case in the agricultural sector, I advise you to consult this particular YouTube video, which shows you an example of the potential of commercial microwave links, particularly geared towards agricultural water management applications, in this case, again, in Sri Lanka. And with that, I would like to close my presentation. Thank you very much for your attention. And again, I would like to indicate that there is great potential for opportunistic sensing techniques, notably commercial microwave links for opportunistic rainfall monitoring and short-term forecasting. But I'm not at all suggesting that this technique or opportunistic techniques in general should replace existing dedicated sensing techniques. Not at all. They should merely act as a complement to dedicated sensing techniques in those areas around the world where the densities of those dedicated sensors are really sparse. So thank you very much again for your attention. And finally, perhaps most importantly, particularly for all the Italian attendants here today, Forza Italia for the finals of the Soccer World Cup coming weekend. Thank you very much for your attention.
Thanks a lot, Remko. Your last wish, I guess it's very well received. Also, I noticed that you moved to the Technical University of Delft from Wageningen, so
correct.
Our best wishes for this new position. So we are open to questions. There are some on the session chat. One is from Anil Kanal. I don't know if Anil wants to make the question directly, or I can make it or I can just read. How easy is to obtain the data from the commercial mobile operators to perform this kind of opportunistic sensing? That's the question from Anil Remko.
Yeah, thank you very much for that question. I stopped sharing my screen. I hope that is okay. So yeah, definitely that is a challenge. As I indicated, we have been working on this subject for more than 15 years actually. Over the years, built excellent collaborations with individual mobile network operators. But obviously, in order to be able to scale this up to, let's say, countrywide and eventually continental scale precipitation products operationally, so in real time, we need to collaborate at the same time with many individual mobile network operators. And for us as an academic partner, so to speak, that was definitely a challenge. And therefore, we started actually this collaboration with the GSM Association a couple of years ago. And actually, GSMA acts in a sense as a kind of knowledge broker between the academic community on the one hand and the mobile network community on the other hand, because actually most, if not all, of the mobile network operators worldwide are associated with the GSM Association. And so we're currently basically working on a sort of country by country basis to develop this further. And we're slowly but surely filling in the global map. And actually what I indicated also during my presentation, it's actually the potential business cases for the mobile network operators, obviously, that would be an extra, let's say, motivation for them to share their data. And GSMA and actually the same holds for us. We think that there is indeed a good business case for sharing these data, even in the global south. Thank you very much.
Thanks, Remko. Actually, the question was from YouTube. So we thank Anil for participating. Then there is a question from Davide Ori, who is actually one of the next speakers. And I don't know if Davide wants to make it directly, since he's...
Yeah, sure. Hi, Frank.
Hi, Davide.
Yeah, my question is actually looking at the communication market, it's very prone to innovation. And innovation is driven by business, basically, there. It's not like science can ask for different things to the communication market. So I want to ask basically same question from two sides. What's your vision towards innovation in the communication market, specifically, for example, 5G, who is upcoming? And isn't there a risk that we are developing a lot of tools that are going to be outdated pretty soon because basically the commercial link are going to be different? There might be shorter and more dense, different frequencies, so different opportunities. Just like a general overview about this topic.
Yeah, thank you very much. That is an excellent question, and indeed, because these technological innovations are mainly driven by business. That is also the reason why in my presentation, besides the scientific aspects, I also stressed actually that business case, because that is really the only way by which we can convince mobile network operators to share their data. And luckily, we're making great leaps with that together with GSMA. I fully agree that there are important developments going on, notably 5G, as you mentioned before. And at the same time, what we're witnessing in countries, for instance, in my home country, the Netherlands, is that the density of the microwave link network is rapidly declining in favor of fiber optics. So in that sense, opportunities in countries such as the Netherlands are expected to decline in the years to come. That said, even, let's say, our partner T-Mobile in the Netherlands expects that there will still be a backbone network of commercial microwave links in the Netherlands with a density that is still larger than the typical density of rain gauge networks operated by the National Meteorological Service. So in that sense, even in the Netherlands, there's future for this technique, particularly in urban areas. Of course, in the global south, that is very different because over there, the development of, let's say, the 4G is still in full swing and is expected actually to grow still very rapidly in the years to come. If you consult, for instance, reports published by Ericsson, their microwave outlook, quite interesting. They expect, particularly in the global south, these networks and their densities to grow rapidly in the near future. So in that sense, there's still lots of potential. And finally, and then I will close off because I see Frank is probably watching the schedule. 5G, of course, is also posing enormous potential for opportunistic sensing techniques, because many of the frequencies that are actually being proposed connecting our cellular devices to nearby antennas are expected to employ radio frequencies that will be affected by precipitation or could be affected by precipitation. So actually, we're also starting to work with some of the commercial partners involved there to see if we can use actually 5G infrastructure also as a means of opportunistic environmental monitoring. So definitely there's business driving the technological developments, but if as a scientific community we're closely, following these developments, I'm pretty sure that there is much to be gained. Thank you very much.
Thanks, Remko. There is a last question by Jordi Figueres. I can read it to be short. Have you attempted to characterize the uncertainty of the measurements as a function of the link density or link length? I guess so.
Yeah, definitely. That has been an important subject. Jordi, thank you very much for that question, of our research over the past 15 years, because obviously for any quantitative application, be it in meteorology, in hydrology, water management, or agriculture, you need estimates with, of course, hopefully a small bias, but also need to be aware of the uncertainties and their relations to, let's say, network properties on the one hand, and rainfall properties on the other hand. So I can point you to several of our papers where we basically investigated this matter in great detail. Yeah, thank you very much.
Thanks a lot, Remko, for your very wide overview on this topic. So I pass the floor to my colleague, Roberto Cremonini, for the last presentation. So please, Roberto.
Thank you, Frank. First of all, I wish to thank Tomo and Remko for the interesting presentation, and a warm welcome to Annakaisa. So in the previous day, we really understood the relevance of weather radar networking. Annakaisa is from Finnish Meteorological Institute. She is the project manager of HumanNet initiative of European weather radar networking. Today, she will give us an update on this very relevant project at a European level. So, Annakaisa, the stage is yours.
Thank you very much, Roberto. Thank you for the introduction. And also thank you for the invitation to join and to talk about Opera here. So I will move now maybe for more technical presentations to descriptions of the network and collaboration. Let me share my screen. Okay, I hope you can see it now well.
Yes, we can see it.
Okay, so in this presentation, I would like to present the current phase of Opera 5, and what is the status and what are the future plans in this program. So just to Being brief, first, what is OPRA? As Roberto already described, it is an observational program under the umbrella of the European Meteorological Services Network, so-called EUMETNET. It was established in 1999 to the foundation of COST 72 and 3 and GORN projects. So more than 20 years, OPRA has coordinated the operational weather radar collaboration among the national weather services in Europe. Basically, the overarching objectives of the program is firstly to provide a platform for the radar specialists to exchange know-how and algorithms for data processing, but also very practical help, for example, in running and monitoring radar network, or for example, in tendering a new radar. 2 times a year, the experts gather to discuss these issues under the expert team meeting. The second objective is to develop, generate, and distribute high-quality pan-European weather radar composite products on an operational basis. And here on the right, you see an image of that, and I think that's very familiar to you all. At the moment, OPRA has 30 members, and our database includes 204 operational radars, of which 163 are C-band, 29 are S-band, and 12 are X-band. And currently, 65% of those are dual-pole radars. The radar data from 166 radars are exchanged regularly, and the composite is formed from 160 radars, roundabout. We are creating the composites every 15 minutes with a 2-kilometer resolution. The products are the maximum reflectivity, rain rate, and hourly rain accumulation. In addition, we are creating quality-controlled volume data for the NWP assimilation. So let me now go back to these 2 objectives of OPRA and share some news related to both from the OPRA 5 phase. First of all, linked to OPRA, the members have organized 2 workshops with the topic of weather radar monitoring and calibration. These have been organized by DVD in 2017 and 19. And now the 3rd one will be organized this autumn by Météo France in Toulouse in November. Here you see the dates, so if you're interested, welcome to join. And these meetings have been very fruitful. The last one we had 60 participants. There's the image of that. And for the first time, we also invited the manufacturers for 1 day. It was interesting to hear their views and recent developments. And also, one of the interesting topics was that we had Japanese colleagues sharing their experiences with solid-state amplified transmitters for calibrating and monitoring procedures with dual-pole radars. After each this kind of workshop, a report is published, and that can be found from our web pages, and you can see the link below. Also, the knowledge sharing objective includes monitoring methods, which we are applying for the whole network. 2 of them are in a routine, a monthly routine. One of them is the sun monitoring routine and the analysis. It has been operational already from 2016. And it is, of course, to see the stability of the antenna pointing and the stability of the receiver level. The method is based on Huuskonen and Holleman, and currently we can provide that monthly results for 105 to 110 radars of the network. What is new in OPRA 5 is the monthly monitoring of the radio frequency interference. This is an algorithm which is based on the unfiltered horizontal reflectivity data, which we can obtain from almost all of our radars. And we are examining all elevations below 1.5 degrees. And the method is based on Baltrad-Radvol quality control code, which is adopted by ZMAG. And the idea of this monitoring is that we would like to see on a network level how vast the problem is at 5.6 gigahertz frequency level, and whether these suggested methods to mitigate the disturbances are efficient or not. So we are following the time series. But because of the technique that we are using, so we can only use the unfiltered reflectivity, of course, the national algorithms can provide maybe more detailed analysis of the situation. So the priority is always there with the national monitoring routines. But with this kind of monthly network monitoring, we are trying to get the time series, what is happening in these disturbances. And here on the right, I just have an image from our FMI radar. Well, we don't have that much of a problem with the RFIs, only on some. Here it has identified 8 emitters in that particular data set. But below you see the network level analysis of 1 year, and we can analyze now 113 radars. And with the red color, dark red color bars indicate the number of radars where 50% of the elevation scans up to the 1.5 elevation were found to show RFI signatures on that day. So that's a daily number. So we can see that it is a relevant number in Europe. And then from the also knowledge exchange, to facilitate the international radar data exchange, the OPRA has developed and sustained the OPRA Data Information Model, ODIM. And it has been implemented both inside and outside OPRA, so it's almost an international standard already. And what is good about it, that of course it's a manufacturer independent, and it's also independent from the organization which is providing the data. Naturally, this model evolves in time, and that's why OPRA is supporting it, so that we can have the new variables and all the new quality related information in the data set. And the newest release was actually last week, the 2.4 version. And you can find the description on our website. Here's the link as well. What is good to mention for that, for example, is that in this 2.4, the new attributes and quantities follow the CF Radial 2 conventions, which is a similar information model from VMO. So the idea in the future is that these both models would evolve closer to each other. Now let me go to the second objective of OPRA. That means the radar data exchange and the production of the quality controlled composites. So in OPRA 5, the main goal is actually to renew the whole production line. This is the picture of the old production line. So it used to be so that the Met France and Met Office were gathering the radar data, and they together produced in Odyssey the composite products and the quality controlled volume products for NWP. And then outside users, external users could use the composites by following the ECOMET licensing agreement and also obtaining it through members. So not directly from OPRA, but from the members. So this is now the image of, or the architecture of the new production line. So now it's divided into 3, Cirrus, Stratus, and Nimbus. And these are planned so that we can kind of serve better the various needs of different user groups. So just to be short, first of all, Cirrus will provide reflectivity composite every 5 minutes, targeted, for example, to nowcasting operations. And it should be operational later this year. Secondly, Stratus and Cumulus, they are forming kind of a data hub. So Cumulus is gathering the radar data from the data providers, and then Stratus is forwarding it to Cirrus and Nimbus, the other production lines, and then also to members. And the idea is that it could possibly replace, in some extent, the bilateral exchange channels. And they both were operational in 2020. And then Nimbus, which will provide then the quality-controlled precipitation composite products, wind profiles, and also the quality-controlled radar volumes for the NWP every 15 minutes. So this is kind of replacing the old Odyssey. And it should be operational in 2022. And as you can see, that if an external user would like to use the OPRA products, this part hasn't been changed. So it still goes through the members and following the ECOMET framework in licensing. There are challenges with this new production line. For example, if you think about Cirrus, where we have to create the composite in 5 minutes, that will give a time pressure to gather the data. And nowadays, many members have started to send sweep by sweep and no longer volume, so that we can get a little bit more time to create the composite. Also, discussion with Nimbus is that what are the quality controlled measures that we are going to apply centrally and what are going to be applied nationally before sending the data. Here we need to be sure that the quality that we have reached in earlier phases of OPRA, that it wouldn't decrease, but rather increase. So this is still under or in progress, let's say it this way. And let me share some insight to that particular part from the earlier phases of OPRA. So the original idea in 2011 was that in order to get as homogeneous product as possible, they collected raw data and all the quality control procedures were done centrally. But as we know, the radar network is very heterogeneous in Europe. We have different scanning strategies in different countries. Applications are different. The age of the radars are very different, from 30 years old to up to date. We have dual pole, we have single pole. So it is really hard to find a centralized mechanism to improve the quality. For example, fixing the sea clutter in Mediterranean actually removed then snow from Scandinavia. And additional to that, during the previous stages of OPRA and also now, members are upgrading their radars to dual pole. As we said, 65% is already dual pole. So nationally, the cleaning procedures can be much more efficient than we can offer centrally. So coming from those kind of conditions, in 2017, it was decided in the expert team that the countries will send the best possible data, best possible reflectivity. So the cleaning algorithms are driven nationally, and it's documented how it's processed, and then the unfiltered data is sent as comparison as a different parameter. And here I would like to share what was the effect of this decision. This work is done by Sinchu Park at the Polytechnical University of Catalonia. She created a real-time gauge adjustment to OPRA data, calculating a daily adjustment factor, comparing OPRA to SYNOP gauges observations. And on the left up image, you see the 24-hour accumulation from OPRA for one single day, 25th of July 2017. And next to that is the SYNOP gauge observations for the 24-hour accumulation. Below on the left, you see the adjustment factor, and you can see the values are deviating from 1 till 3.6 maybe. The upper threshold is 5. Higher than that are not corrected. And then on the right side below, you see the OPRA 24-hour accumulation adjusted with this correction factor for that particular day. On the right side, you see a time series of the radar to gauge comparison, or ratio radar to gauge. And with the red colors, you see the after the adjustment, so corrected estimate, and with the bluish colors, you see before the adjustment. And I'll show here only the years 2013, 17, 18, and 19 in order to have bigger pictures. But Sinchu has driven this algorithm for the data since 2013 up till now. And you can see from the 13-17 that the ratio was, as a mean value, it was 0.7. So OPRA was underestimating the rainfall amount. But after this decision in 2017, in March, countries slow by little started to implement and send the best possible data. And you can see very clearly in 2018 how the comparison changed. And nowadays, the factor value or the ratio is typically the mean value is 0.9 to 101. Here, please note that this is affecting only to the summer precipitation. For the winter time, OPRA is still applying a single ZR relation, so we are not considering the snowfall. And also gauges have problems with the undercatchment with the snow, so this is more relevant to the summer rain. Also, other users have reported the improved quality after this decision. And who are the other users of the data? Well, naturally, the primary user communities are in meteorology, hydrology, climatology, aviation, but also there are communities like biologists who would like to use the data for studying bird and insect migration. For the European NWP communities, most of them already assimilate national or near neighboring radar data operationally to their models. And now, I think little by little, some communities have started to also assimilate OPRA data, at least pre-operationally. Typically, they assimilate the both reflectivity and the radial velocity. But as an exception, European Center is assimilating the composite product because they are following the similar process they have for the NextRad radars. And according to them, with the improved quality, also the recent evaluations show some positive results. One more example of the use of the OPRA radar data. So this is work done by Maud Martet at Météo France, and they have assimilated OPRA data to AROM operationally since 2020. And you can see here in the image with the red stars is indicated the OPRA radars that are assimilated to the AROM. The input data that they are using is the before mentioned best reflectivity, then the raw reflectivity, and that means kind of meaning Doppler filter total reflectivity, and then radial velocity. And the difference between the reflectivities is used to distinguish the points of no rain. And additionally, they utilize in this process a called quality index, which is calculated from the centralized processing of what we are doing in OPRA. So we're not completely abandoning the central processing algorithms. We do drive some of them, even though we take the best possible data. And a quality index is calculated from those, and that's applied in the process to filter the non-met echoes. Coming back, in the evaluation, it looks like that their improvement could be seen in a 6-hour accumulation, but a neutral impact was seen with the longer time period with the 24-hour accumulated precipitation. And here's a case example from Maud. You can see in the image where there are observations, if you can see my cursor here, image on the left, that's a rain gauge product of antelope showing the 24-hour accumulation. And then on the right is the model, the model reproduced 24-hour accumulation, and without OPRA radars, and below it is with the OPRA radars. And here the Spanish radars are used. And you can see that in this plot, the high intensity or the high amounts of precipitation in the south coast of France cannot be reproduced with the model if OPRA radars were not assimilated. So let me summarize my talk. So I was presenting the two main objectives of OPRA. The first one was to provide a platform for a knowledge exchange related to operational weather issues. And in OPRA 5, we have organized workshops, performed network level monitoring, and to facilitate the data exchange, we are sustaining the ODIM data information model. And the second objective was to provide high quality radar composite products to on an operational basis. And in OPRA 5, we are renewing the whole production lines and hopefully to serve better the different needs of different data users. So I thank you now for your attention, and I'm ready for questions if there are any.
Thank you, Annakaisa, for your interesting presentation. So it's time for question. I have a question. As OPRA community, are you taking action against RFI interference? Because it's a huge problem in Europe. So I'm wondering if, as a community, you have more power to.
Yes, I mean, UMetNet has UMetFrec, which is the frequency kind of organization trying to protect the frequencies that are important to the Met institutes. And this tool that we actually planned it in a way that this monitoring tool, we are providing these statistics really to UMetFrec so that they can report how big the problem is actually, and also give kind of a time series and constant analysis that if it's claimed that these suggested mitigation processes should affect, we could show whether they actually affect. So we are trying to create some pressure in that sense as a community to help. Whether it works, let's see, but this is the meaning.
So we are waiting still for some question. There is time. Otherwise, I have another question about X-band radar in Opera network. So these weather radar are really different from the performance. So technically, and the quality of data that they produce can be very different. So what is the position of Opera about X-band radar, or what's the line of investigation?
I would see some countries, I mean, mostly they are Météo France X-band radars that are in the network. I don't think that there is, from the Opera point of view, that we would recommend something or not recommend something. It is a national decision. And we do welcome all the data also. Of course, we do have some quality issues that we need to take into account. If we see that the quality is not enough high level, we might exclude them from the composite. But having said that, we also have the very old radars and we are still accepting them. So I don't want to say it's too strong opinions. I think that's a decision of the National Met Institutes, and if the quality is reasonable, we gladly welcome them to the network.
So thank you, Annakaisa. And then I think...
Can I make a last question?
Yes.
Just to Annakaisa. Hi, Annakaisa. Is there any plan to enlarge the consortium or also to enlarge the coverage, the radar coverage of the consortium? We notice that the Southern Europe, for instance, is less covered than the Central Northern Europe.
Yes. There are two levels of decision here, of course. There's the political level, and then there is the technical level in a way. From the technical level, Opera, of course, welcomes all the new members and would like to have better coverage, but that the decision has to be done in the political level first. Having said that, we are open to test data to see whether it is, if we can implement it to our production line easily. We are open for that and testing, and that way to diminish the technical barriers. Political, that's then we're discussing things, but that's on a higher level.
Thanks, Annakaisa.
So we are almost in time. So I wish to thank all the speakers and thank you for this interesting session. The session is closed, so I move the talk to Frank, if you want to add something.
Thanks to all the speakers and also to the organizers. So we can leave the floor to the...
Yes, I think it's time for some technical instruction for the next break.
Good morning. Thank you very much for the very interesting talk from the speakers. Now it's time to have the little break. We are a little on delay, accumulated a delay of 5 minutes, so we think that we can have a shorter break of 25 minutes till 11:30. Now is also you have the possibility during the break to join the factory rooms. You can see in the interface of Zoom the possibility to access the rooms where you can find two factory, Eldes and Euroelettronica ICAS. So you have the possibility to access these rooms. From the YouTube sides, you will not be able to access this room, but you will see the streaming of some video. So we will wait for 11:30 to restart the streaming. So thank you and see you later. un radar meteorologico è uno strumento estremamente utile durante le fasi di vigilanza meteo. Un radar è in grado di monitorare la precipitazione nell'arco di 100-200 km e consente di localizzare i sistemi più intensi e di caratterizzarne la dimensione spaziale. Qui vediamo un composito di vari radar meteo, quindi coprono un'area molto estesa e come vediamo possiamo visualizzare la precipitazione attraverso una scala di colori. Il colore meno intenso è il celeste, poi il verde, il giallo, l'arancione e il rosso danno informazioni sull'intensità sempre più crescente della precipitazione. Inoltre le zone che noi vediamo rappresentano l'estensione spaziale della precipitazione. Dall'animazione di varie sequenze di immagini noi possiamo andare a vedere come i sistemi precipitativi si evolvono nello spazio e nel tempo. Quindi possiamo vedere quali sono le aree che sono via via interessate dal passaggio della precipitazione e quindi stiamo effettuando un'operazione di nowcasting, ovvero possiamo predire ciò che succederà nell'arco delle prossime 3-6 ore. Quest'anno il Convegno Nazionale di Radar Meteorologia è organizzato dal consorzio LaMMA. Non è un caso che il convegno sia organizzato da un centro di vigilanza meteorologica, proprio perché questi strumenti sono di estremo aiuto durante le fasi di allerta e di vigilanza meteorologica. Durante il convegno si riuniscono infatti operatori in ambito di radar meteorologia che condividono le proprie attività di ricerca e i risultati ottenuti, oltre che condividere anche attività per la definizione di nuovi sistemi utilizzati operativamente.
Radmet2021.it è il quarto della serie di convegni nazionali di radar meteorologia iniziata nel 2015. I ricercatori come me, io sono un ricercatore del CNR, Istituto di Scienze dell'Atmosfera e del Clima, uno dei promotori di questi eventi, hanno molte opportunità di poter confrontare le proprie ricerche con quello che fanno i colleghi in tutto il mondo. Però è soltanto in questi convegni di carattere nazionale che è possibile confrontarsi con e soprattutto su tematiche di interesse nazionale con chi con i radar meteorologici fa ricerca, chi li usa per svolgere al meglio i propri compiti istituzionali, ad esempio il Sistema Nazionale di Protezione Civile oppure gli enti meteorologici regionali, ma anche con l'industria nazionale. In questi convegni in genere si parla italiano, ma quest'anno per la prima volta ci sarà anche una sezione internazionale nella quale si parlerà inglese. Abbiamo infatti invitato colleghi di fama internazionale che volentieri hanno accettato l'invito di venirci a trovare e ovviamente verranno a trovarci in forma telematica, e alla fine è venuto fuori una sessione che molti congressi internazionali potranno solo invidiarci.
È una conferenza importante perché tratta in maniera esaustiva lo stato dell'arte del radar meteorologico in Italia. Inoltre affronta anche altre tematiche, ad esempio quella dell'integrazione del dato radar con le osservazioni provenienti da altri sensori, ad esempio quelli posti a bordo dei satelliti meteorologici. Queste informazioni possono dare importanti contributi su vari fronti, dalla stima della precipitazione all'identificazione dei sistemi meteorologici più intensi. RadMet dedica un'intera sessione della conferenza a questa tematica, che si intitola appunto Radar meteorologici e altri sensori, sinergie e o interferenze.
Il Consorzio LaMMA è particolarmente contento di ospitare questa quarta edizione del Convegno Nazionale RadMet 2021. 2 anni fa, quando ci proponemmo come sede ospitante, non potevamo pensare che ci sarebbe stata la pandemia come è successo. Questo purtroppo, come sapete, ci costringe a fare il convegno online in streaming. Vediamone quello che è anche i lati positivi di questo. Probabilmente ci permetterà di avere una maggiore, partecipazione, una maggiore partecipazione sia in termini di contributi, ma sia in termini appunto di persone che seguiranno il convegno. Da un certo punto di vista forse anche ridurrà quelle che sono le emissioni di anidride carbonica, in quanto ridurremo appunto i viaggi per arrivare a Firenze. Forse lo svantaggio è che non potrete godere di questa bellissima città quale è Firenze, come ci avevamo proposti proprio appunto per permettere a tutti voi appunto di poter visitare la nostra città. Questo convegno naturalmente è un elemento importante per la radar meteorologia, è un momento di dialogo, di confronto, di scambio di esperienza su tutta quella che è la comunità di esperti e ricercatori nel campo della radar meteorologia. Il radar è sicuramente uno strumento essenziale, indispensabile per un servizio meteo operativo quale è il Consorzio LaMMA, che rientra nel centro funzionale della regione toscana, e come sappiamo è uno strumento che è praticamente unico nel suo genere per poter fare il cosiddetto nowcasting, cioè vale a dire previsione a brevissimo termine, e quindi poter seguire l'evolversi di tutti quei fenomeni che possono arrivare a determinare condizioni di temporalesche o di previsioni piuttosto intense su quello che è il nostro territorio. Con questo vi saluto e vi auguro un benvenuto al RadMet 2021.
Che cos'è radmet.it? È il convegno nazionale di radar-meteorologia, figlio naturale dell'ERAD, la European Radar Conference, nata nel 2000. L'ideazione del convegno nazionale di radar-meteorologia ha origini quasi leggendarie. Infatti, in un imprecisato pomeriggio della prima settimana del 2014, durante l'ERAD di Garmisch in terra teutonica, si narra che in modo carbonaro un gruppo di persone si riunì per avanzare la proposta di chiamare a raccolta danni alterni in modo complementare rispetto ad ERAD tutta la comunità nazionale radar-meteorologica, dagli enti di ricerca universitari agli enti istituzionali e operativi, dagli esperti del settore ai decisori politici e agli attori industriali. In sostanza, l'idea era quella di creare una grande piazza dove fare il punto sullo status della tecnologia e della ricerca in radar-meteorologia e delle sue principali applicazioni in ambito ambientale e civile. In quel pomeriggio nacque dunque il convegno radmet.it, che divenne in realtà a Roma il 2 luglio del 2015 presso la facoltà di ingegneria nella cornice di San Pietro in Vincoli. La partecipazione fu entusiasta, con oltre 150 persone, vari espositori, e da quella prima edizione il resto è storia, che passò per il Dipartimento della Protezione Civile Nazionale nel luglio del 2017 e poi per l'ARPA Piemonte a Torino nel luglio del 2019. E oggi siamo a Firenze insieme con i colleghi del LaMMA e del CNR, seppur in forma telematica visto il contesto pandemico. Ma nell'anno di Dante potremmo dire quale miglior sintesi tra scienza, tecnologia e arte nel nome di radmet.it.
Radmet è un'occasione di incontro tra la radar-meteorologia e la modellistica numerica. Nonostante il miglioramento della risoluzione e della fisica dei modelli di previsione, la previsione della precipitazione infatti è ancora soggetta ad errori sia nella localizzazione che nel quantitativo. L'assimilazione dati, che combina modello ed osservazioni, permette di migliorare le condizioni iniziali da cui partono le previsioni. In particolare, nell'assimilazione dati a scala convettiva, i modelli numerici di previsione ad alta risoluzione richiedono osservazioni ad alta densità spaziale e temporale. Per questo motivo, i radar sono diventati di importanza strategica per la modellistica numerica, in quanto forniscono l'osservazione di ampie porzioni di atmosfera con elevata frequenza temporale.
Buongiorno. Ritengo ci siano diversi buoni motivi per partecipare a Radmet 2021. Innanzitutto è l'occasione per comprendere il ruolo dei radar meteo nelle applicazioni operative, con particolare riferimento ad attività di monitoraggio e previsione a breve termine nel contesto del sistema di allertamento nazionale. Poi è anche l'opportunità per verificare che si tratta di una tecnologia matura, pur nella consapevolezza dell'incertezza ad essa associata, eventualmente sfruttando l'enorme potenziale derivante dall'uso dell'intelligenza artificiale, anche questo argomento che sarà oggetto di trattazione a Radmet 2021. Per finire, Radmet 2021 offre l'occasione di analizzare nel dettaglio alcuni eventi particolarmente severi che hanno interessato il territorio nazionale. In altre parole, sarà senz'altro un evento di eccezionale interesse per tutti.
let's start with the next session. I would like to pass the line to Paolo Alberoni. I don't know if Paolo is present.
Yes.
Okay.
I'm here.
Okay.
Thanks, Andrea. I'm glad to welcome all of you to this second session of the International Day of RadMed 2021. And so we can start the session now. The session is addressed to radar nowcasting and precipitation retrieval. And the first speaker is Ioannis Sideris from Meteo Swiss that we talk about NowPrecip. Ioannis. I'm sorry, Ioannis. I'm a bad boy.
Thank you very
Please
much.
Apologize me.
No, of course. Thank you very much for inviting me. I would like to thank all the people in the audience. Let me see if I can share correctly my presentation. Can you?
Yes.
You can see the presentation, right? And let me make this disappear. Okay. Today we're going to talk about NowPrecip. I'm Ioannis Sideris. I'm from Meteo Swiss, Locarno Monti, in the radar group of Meteo Swiss. NowPrecip is a new application. It's precipitation nowcasting system. It was we developed it relatively silently in the past few years, and it became operational only last year. So it's a new application. The evolution you see, it is straight from the Meteo Swiss app. I would like to see you to see that we have made lots of effort to make it as realistic as possible. It looks like radar. It's not radar. It's a nowcasting product. The spatial resolution is 1 kilometer, temporal resolution 5 minutes, and the forecasting horizon it's 6.5. As an aerial nowcasting system, it concerns the entire domain of the radar. We're not talking about an object nowcasting system. It's aerial nowcasting. It is probabilistic. It is based on stochastic noise, which means that it can produce an ensemble. It has a merging mechanism with NWP. It has growth and decay mechanisms. These mechanisms, many times, they are missing in other nowcasting systems. They are kind of difficult to include. And we have done lots of effort to make it as seamless as possible, without jumps, to make it realistic and to make it to increase the local adjustment. We have a local adjustment control, which you're gonna see in the next slides, which again is missing from other systems. In general, the aerial nowcasting systems available, they are divided into two components. The optical flow, which is responsible for constructing a motion field based on the last few observations, and then the extrapolation part, which extrapolates the last observations into the future. We want to talk now about the optical flow we use. It has a sort of innovation there. So what we do with the optical flow is to choose randomly some hundreds of points, 200-300 points, and use a typical pattern matching or block matching to see how these points will move in the future. We use the last couple of observations of the radar to do that. And it is not new, this technique, it is old. But then, in order to tie everything together and produce a motion field over the entire radar domain, we use kriging, which is new. So the name of this new system is NowTrack. When we use kriging, we translate all these hundreds of vectors into a motion field over the entire domain. And although this case is easy here. This use of geostatistics has shown to be able to capture very localized effects. It's very sensitive with small error, and taking into account that many errors in these nowcasting systems, they are coming from a bad motion field. I think it is something that at least in Switzerland we need it. I'll give you 4 different examples of how all this works. You see the stratiform situation, easy situation here on the top left. Top right, we have a convective situation with small cells. You see that it keeps working okay. Then we have some orographic effects exactly at this point. You see that the vectors, they are long, and then suddenly, because of the orography, they start decreasing, and we have a small rotation here, which is captured. And here, I kept for last one the most difficult case. If you notice what happens inside this very small area, it's about 40-50 kilometers in size. We have actually a rotation, a local rotation. The other systems probably they are not able to catch that. They smooth this motion. The NowTrack was able to track this, and you see the vectors moving all around this point. So we have this motion. Of course, the motion field you see I show here is static, but in reality within NowPrecip it is dynamic. It starts from a motion field that looks like this, and then we use the NWP to make everything dynamic. So the NWP enters the motion field and it creates a dynamic optical flow that is changing through the 6 hours of the horizon. The second part is the extrapolation. There we use an autoregressive model plus spatially correlated noise. All this is taking place in a transformed space. So these are the last 2 observations in a transformed space. We add some color noise. The color noise depends on how the last observations look like. Sometimes it's more grainy, sometimes it's smoother, and we end up to the next frame. All this is happening in 1 kilometer scale. After the back transformation, we get this picture, which still doesn't look like weather. And here comes the innovation and in the architectural design of NowPrecip and the difference with other systems. NowPrecip works on both 1 kilometer scale, as you saw before. So the texture is 1 kilometer scale, but it is followed by a localized adjustment, which takes place in a 64 kilometer scale. So we control every one of these red boxes on the raster. We control completely through 2 parameter values, the IMF, which is the mean value of the box, and the fraction of wet pixels, how wet is this area. And when we apply this adjustment, which is based on Lagrangian persistence, of course, we translate all this strange picture into something that looks like weather. Okay, and eventually it looks like this. So I want you to pay attention to this feature because it gives the system a very nice control over very small areas. For example, if you see these 2 pictures, the surroundings of the central box, they look pretty much the same. But by changing the values of these 2 parameters I mentioned within the central box, we take 2 completely different realities. If you compare what happens inside the 2 boxes on these 2 panels, it is completely different, while the surroundings, they stay pretty much the same, which of course, apart from other advantages for growth and decay, it may be a very good mechanism to bridge object and aerial nowcasting. And I'm saying that because at this point, NowPrecip gets information from Cosmo, from the NWP, fine. Cosmo enters NowPrecip in several points. But what we want to do in the future is to combine information from radar thunderstorm nowcasting. There is a program TRT in Meteor Suisse over several years, and it does the object nowcasting based on radar. And there is another one, the coalition, which does thunderstorm nowcasting based on satellite. And we want in the future to introduce information from these object nowcasting systems into NowPrecip, and because NowPrecip has by design this ability to change very small 64-kilometer scale areas within the raster at will, it is possible that we can do that. This means that we can provide meteorologists with a consistent, not only a seamless aerial nowcasting system, but a consistent system which works as a platform of all the precipitation nowcasting systems. The strong point of NowPrecip is in the orographic precipitation. Orographic precipitation is well known. It is based on air that rises and cools. And then when it cools, precipitation is formed, and you have the precipitation only on one side of the mountain, while on the other side, on the lee side, you have pretty much nothing. And of course, when you see that in the radar, what you see. Here is the orographic precipitation. What you see is that the precipitation stops at some point and it doesn't continue. And we wanted to find a way to make this happen. Half of the job to do that is to have a very good motion field. Here you see the vectors. They are long, but then when they approach this area, they become smaller and smaller. And this is because of the orographic precipitation. This is not all. You have to find also somehow the growth and decay. In order to find growth and decay, we use the NWP, because the NWP uses all the variables and it knows actually where growth and decay is going to happen in the future, especially when you have a complex terrain like that of Switzerland. Here you see a map of growth and decay. Blue signifies decay, red signifies growth. And you see clearly that in this area over here at the border of Italy and Switzerland, we have decay. These two components, a good motion field and the growth and decay map, they work together in order to provide the final animation, the final nowcast, where you see clearly that in this area, in the border, the precipitation stops. It doesn't pass the border, and it shouldn't pass the border. Okay. Here is a merging mechanism we have. The merging mechanism is relatively simple but powerful. It is based on Cosmo and nowcasting, on weighting these two components. As we proceed in time, Cosmo, the NWP, is getting a bigger weight, nowcasting a smaller weight. But the innovation in this particular module is that how fast the merging is going to happen depends heavily on how well the NWP correlates with the last available observation. So if it correlates well, we have good reasons to believe that Cosmo has done a very good job. So we merge the nowcast, the NowPrecip, with the NWP faster. If not, then it happens slower. It is a simple mechanism, but it does a very good job. If you see here, here is the black line is the NowPrecip and the red line is the NWP, and you see that the merging is very smooth. You don't have effects, for example, that the nowcast goes below the red line and then it returns. Okay. I said also that NowPrecip can produce an ensemble simply because it is based on stochastic noise. It can produce several scenarios, and each of these scenarios, they merge seamlessly to one of the members of the NWP. And here, and I'm going to close with that, is I have put one example, one movie. On the left, it is the nowcast. It starts from the observation. And on the right, it is the reference, the observation. And in this particular case, you will see that the precipitation stops again here, close to the border of Switzerland with Italy. And you please have an eye also on the observation to see that it does exactly the same thing. And of course, as it evolves, it becomes more and more NWP. It starts from the radar and it becomes NWP at the end of the evolution. If you see I chose some measures. Correlation coefficient, black is NowPrecip, red is the NWP. You see here that it seems that we have skill for something like 4 hours. It's not always 4 hours. In convective cases, it is shorter. But also, if you see different measures, if you examine different measures in this business, you're going to see that they say that there is skill for different times. Here is a root mean square factor by Golding 98. This is a multiplicative error, really. And again, it shows that the error of NowPrecip is smaller than that of the NWP for about 5 hours. And here is the fraction skill score, very useful score. It's from the neighborhood verification section, this one. And again, it shows that there is skill for about 4 hours. So, in summary, we have built NowPrecip with the Swiss terrain in mind. I think the people who, countries that have mountains, especially countries that have mountains, they will be benefited by this system a lot, because we have built it with this in mind, with orographic precipitation in mind. And you saw that it works in such a way so it doesn't allow the precipitation to pass a certain point. It's not an accident. We have worked on that to make it happen. It has a dynamical optical flow, the now track. This is Kriging-based and it is new. Kriging-based has several advantages because it can find automatically all the small effects, the small scales that are of interest. It has also one more advantage, that it comes, any Kriging system comes, gives us as an answer an estimated value and the variance. So we are considering these days how to use this variance, maybe as an error. It has localized architecture. It gives us a very nice control over small boxes inside the domain. This is heavily innovative. It is deep in the heart in the design of NowPrecip, and it is something that I haven't seen in other similar systems. It gives you an advantage also when there is different weather in different parts of the country. If you have convection on the south, stratiform on the north, it keeps the convection on the south. It's not going to generate cells on the north where they don't belong. It has a dynamic growth and decay mechanism, which is based on radar and NWP. Observe that NWP enters NowPrecip in 3 points: in the merging, in the optical flow, and in the growth and decay mechanism. That's why eventually we have very seamless evolution. Okay, seamless merging with NWP. It is probabilistic, of course. We don't produce ensembles yet in MeteoSwiss, but we will in the next year or two. But it is capable. It's ready, and has, this is important, has the potential to bridge aerial and object nowcasting in a single platform. This is one of the holy grails of nowcasting, precipitation nowcasting. And I think based on this architecture we can actually merge object and aerial nowcasting relatively easily with NowPrecip. And the last thing is that it is still in its infancy. We designed it. I designed it like for 4 or 5 years, but only now it appears, and I think it has great potential in the future to do great things. There are 2 papers. The one extended abstract in Holland some years ago, and the official one where we describe in detail all the mechanisms, all the modules. In 2020 QJRMS paper. That's all. Thank you very much.
Thanks, Ioannis, for the very, very interesting presentation you have done.
Welcome.
I just introduced my co-chair, Luca Baldini. So, Luca, if you have, if you see any question.
Yes,
otherwise, I see.
No, I see a couple of raised hand in order. Renzo and then Virginia. They can use their camera and telephone and microphone.
Actually.
Okay. Okay, Ioannis, thank you for the presentation. I like it very much. I think it's a great different approaches, like the analog forecast and the more traditional extrapolation. I have a very quick and technical question about the merging. You mentioned that you allow the merging to vary based on the NWP correlation, and yes. I'm wondering why not considering also the radar correlations. I mean, in the extrapolation nowcasting, in the autoregressive model, of course, you have it is based on the autocorrelation. The autocorrelation may change depending on the event.
We have the radar. The radar is the most recent observation, right? And what you can consider there is how well the NWP matches with the radar. If it matches very well, it means simply that Cosmo has done an excellent job. You have all the reasons to trust this Cosmo, and you have all the reasons to do the merging fast. I mean, because you trust it. It's a good model. So from then on, I mean, radar against radar. I mean, it's. I'm not sure. Is it clear?
No. Yes. I mean that also radar. You may have a higher correlation with past observation or poorer correlation. So you may also give a high weight to the radar in the merging longer if the radar itself is very highly correlated with past observation. But I think it's the same. You either fix one and or the other one.
Okay. You talk about the last observation versus previous observations, and no, we don't do that. What we use entirely the NWP, and actually we compare the NWP with the last 6 observations, the last hour. And yes, it's not just the last observation. Technically, it's the last hour, the last 6 observations, 10 minutes. And this seems to work in the merging, in the skill, extremely good.
Okay, thank you. It's clear.
Very welcome.
Thank you. Now, please, Virginia, ask your question.
Yes, Virginia.
Hi, Ioannis.
Hi, Valentina.
From the NWP side, what is the frequency of NWP runs?
The frequency, you mean how often they are produced?
Yes.
Okay.
To make the merge then after you have the forecast.
They are produced. This one we use now, the Cosmo 1, it is produced every 3 hours. And it has a resolution 10 minutes. Okay. So, or 5 minutes. I mean, it depends what we choose. But it is every 3 hours, and we use the most recent NWP available. Okay.
Okay.
Yeah.
Thank you very much.
Very welcome.
At the moment, I don't see any other questions. No hands. No. So we can thank Ioannis for the nice presentation and for the replies to the question. Thank you. I will pass to introduce the next two talks. Most of the Italian weather radar community is more focused at the moment, because we never know in the future on precipitation measurements, rainfall at ground, but that of ice process. So looking at ice clouds using radars that are not necessarily the one that we use operationally has gained a lot of interest recently. So this is what Davide Ori from University of Cologne, but let's say with some roots in Italy, and let's say so. And I invite Davide, not David, to take the lead and start with his talk.
So thanks, Luca. Ciao anche a Paolo. Very good pronunciation of my name. Very perfect.
I think you are no more used to that. Maybe some
no,
David, yes.
Germans are fantastic about that.
Okay, good.
So good morning, everyone. I'm Davide. I come from Bologna, and I'm a researcher at the University of Cologne. And today I'm going to talk about how to use combined modeling and observational approach in order to better understand ice cloud microphysics. I want to start by acknowledging the contribution of my super colleagues working at the Optimize research group, starting from the group leader, Stefan, and his current two PhD students, Marcus and Leoni. But a great thanks goes also to Jose, who recently got his doctoral degree and moved to Delft, Frederick, who is now in Clermont-Ferrand. And I technically do not belong to this group anymore, but I'm still at the University of Cologne. Nonetheless, Giovanni came in as a new PhD student in the group, so the group holds its fair share of Italians nonetheless. Optimize is actually a meaningful acronym, but I can't really unroll it by heart. However, you can intuitively understand that it means something about using different techniques like weather simulations, snow particle modeling, and observation in an optimal way in order to gain some information about ice properties. So the question is, why ice? Well, statistically speaking, vast majority of precipitation at the ground is actually initiated in the ice phase in the cloud. Therefore, it is only natural that one wants to know as much as possible of the ice in the clouds. But this is what we can call scientific motivation. Truth is that, honestly speaking, snowflakes are quite attractive, not just the most perfect crystals that you might post on your Instagram page, but they are all fantastic in their own way. So beautiful that actually people looked at them since a long time, which is an activity that was requiring to stay for quite some time in a rather unpleasant weather situation, performing very repetitive tasks just to take a picture of them. Early scientific studies, like the one from Nakai and Tereda, studied the mass-size relationship of snowflakes, and those are the perfect example of what can be called a manual observation. Because in order to measure the mass, they actually had to put their finger under the collection paper and melt the snowflakes using their own hands as a heating device. For example, this is one of the first mass-size plots that you can find in literature, and although it's really old, you can already see by noticing that this is a logarithmic scale that there is a very large variability in natural snow properties. Of course, nowadays we enter the so-called, or at least I call that, video imagers era, where it is possible to use advanced automatic cameras in order to collect snowflakes images and measure their properties in an automatic way. But that's not the end of the story, because imagers can only see snowflakes from a side or more than one. And for irregular 3D shapes, basic geometrical quantities are actually not well defined. Moreover, those quantities will depend on the view angle and fall orientation of the particle. Not to mention that some volumetric properties, such as the mass, is very difficult to measure. And although there are some advancement towards that problem as well. So we still have problems measuring snowflakes, but don't panic, because whenever we have a problem in an empirical study, we can just gently move the problem to the methods section of our paper and develop a model. And nowadays we have a model for snow aggregates, we have models for snow rhyming, and they even have models for snowflakes that are melting. And these models have a lot of great qualities. For example, they give you access to the full 3D shape. Any structural quantity is clearly defined, and it happens that the modeled properties match the observed ones quite good. There is a review from Tinela and Von Lerber from a few years ago precisely about that. You can run your model as much as you want, and you can just sit on your desk chair having a good coffee, which is a much more relaxed situation. One thing that is great about having access to this complex 3D shape is that you can simulate the interaction of snowflakes with electromagnetic waves. Here you see an example, and we use different models, among which the discrete dipole approximation is actually by far the most popular. But the problem is that with these methods, those are very, very computationally expensive. So we get just a limited number of simulations done. However, scattering computation have already revealed that there is a huge variability in the snowflake scattering properties. Here you see an example. Again, look at the y-axis logarithmic scale. This means that there are order of magnitudes among the various scattering models. And more interesting, this variability is frequency dependent. You see some reference XKA and W band vertical lines. This is basically the basis of radar multi-frequency observation, where we measure reflectivity at more than one frequency, which individually they depend on the backscattering and concentration of particles. But then we compute the so-called dual wavelength ratio, also known as dual frequency ratio, depending on your preferences, which is totally independent on the total concentration of particles. And it basically increases as the mean size of the particles that you are looking at. But if you remember, all of these are frequency dependent. So what we can do is to add a third frequency. So we compute the dual frequency ratio in two different frequency pairs, such as KW and KUKA or XKA. And what we see is that different particle types actually populate this so-called triple frequency plot in different areas. So there is a hope to distinguish particle types depending on their structural properties. So we now want to use these scattering properties to simulate radar reflectivity. But the problem is, as I said before, this scattering computation are very expensive. So we just have a handful of particles simulated per particle type. And we cannot be really sure that this represents natural variability. At the same time, we also saw in recent years that there are many more scattering databases published. So the question is, which one should I pick in order to make my simulations? Or just to be a little provocative, can we just average them all and take like a mean snowflake as an example? So I want to introduce you to a different approach here. And first I need to just briefly introduce the Rayleigh-Ganz approximation, which is a scattering approximation that basically neglects interaction between the different parts of a snowflake shape. And it can be written as a normal Rayleigh coefficient multiplied by a form factor, which takes into account all the phase delays among the electromagnetic wave, which for a single particle adds coherently. So basically this form factor is solved as an integral over the particle volume. So it's something which we can compute for single particles. But then we also have to remember that whenever we use a radar or any remote sensing instrument, we look at the particles ensemble simultaneously. So many individual particles at the same time. So the idea from Westbrook and Hogan was to fit a model for the irregular particles, which comes directly from the mathematics of fractals. I will skip a lot of mathematics here because, it's pretty long. But basically what you can intuitively get is that we take a lot of particle shapes, we average them all, so we get a mean shape. And then because the snowflakes exhibit snow fractal properties, we fit a power law to the fluctuations of each individual snowflake shape with respect to the mean. Bottom line, we have a formula that gives us radar backscattering for each particle type depending on only 4 parameters, which are derived from the structural properties of snow. And what is even better is that if we compare these properties with those calculated with more advanced models, such as DDA from some earlier slides, we see that actually the biases between the two models are very, very small, up to a quite large frequency. And there is a code publicly available and a reference paper from this year, actually, it was published this year, which is called SnowScat. So you can download it. And what is even better about this code is that it comes with batteries included. So we already derived many parameters for many different particle types. And what you can do is to take it, calculate scattering properties, and perhaps even plot some triple frequency plots like this one, where all of these particle types are individually evaluated. Okay, so that sounds great. We have enough of modeling, so we also run multi-frequency radar observation. For example, this is a data set which has been published, is already quality controlled and processed, and it's available to the public. So again, you are very welcome to download it and use it for your own works. It comes from the TRIPEX campaign, which has been held for 2 months in winter 2015. And we got reflectivity from 3 collocated vertically pointing radars at X, Ka, and W band. So what you can do when you have rather long observational basis is to take a statistics out of it and connect that with the expected scattering properties that we got from the previous modeling study. So the next thing that you might want to do is perhaps take a weather model, so NWP, in our case, ICON LEM, with true moment microphysics, and an instrument simulator, and use those scattering properties to simulate reflectivity at multi-frequency. And I have to spend a few words about the microphysics, because microphysical schemes determine cloud evolution in weather models, and we used already a quite complicated one. It's a two-moment microphysics with 6 hydrometeor classes. Although complicated, it's not actually matching the complexity that we see in the natural clouds, because it has to rely on parameterization for the properties of each different particle type. As an example, it uses power law coefficients for the mass size and the velocity size relation. So how do model and observation compare? They actually compare pretty well. So here you see time-height plot for reflectivity at 3 different frequencies. The dynamics of the weather is very well captured, even the timing of the precipitation at the ground, and the various sensitivity of the 3 different instruments are also well represented by our simulator. So since we have actually a good matching of the weather for many different events, what we can do is to move to the statistical analysis and make histograms of measurements at multi-frequency. What you see here is basically a 2D histogram of DWR at 2 different frequencies distributed according to temperature. And you remember the key to interpret these plots is that if DWR increases, it basically means that the mean size of the particle also increases. So what we see if we compare the observed and the measured one is that actually for the measured, the DWR starts increasing a little earlier, between -20 and -15, where we expect to have dendrites growing, so crystal types that are very likely to form aggregates. But then the model picks up quite fast. DWR increases very fast, and it reaches often the saturation point for KAW, but even XKA actually very often goes to very large values. So basically, it means that in the model, there is a process in the clouds that actually generates very large snowflakes in the model. So what we can also look at is the mean Doppler velocity, because we have vertically pointing radar with Doppler capabilities. What you can compare again mean Doppler velocity at various frequencies and temperature. Here I put a vertical line to mark the -1 meter per second just to guide your eye. And what you can see is actually that the modeled mean Doppler velocities are much larger than the observed ones. That is something that you can also look at if you plot the histogram of the mean Doppler velocity with respect, for example, to the DWR, which you can roughly interpret as a reflectivity-weighted mean velocity size relation. So what we see from these combined plots is that actually in the model, the snowflakes are falling much faster. And due to the theory of differential deposition, if we have a larger range of fall velocities, we expect that actually aggregation is enhanced. So it only makes sense that we have larger particles. Okay, so just to recap, we have a tool that makes possible to make scattering computation on multi-frequency. And when we apply that to a observational campaign, we saw differences between the parameterization that we imply in the model and the observed statistics of particle properties. So what now? Actually, I didn't told you part of the story, because something that you can do also with the 3D shapes of snowflakes is to calculate with some complex hydrodynamic models their fall trajectory, for example, or even you can print them in a 3D printer and make your own snowflake action figure. You can sink them in a tank and see actually in an experimental setup, thanks, how do they fall, what's their fall trajectory. But again, this is very time consuming, so we prefer to use approximations because we do not care about fall trajectory, we just care about terminal fall speed. And what we see is that we can make fits of fall speed velocity size relation using large particle ensembles. So also, I didn't told you that also these velocity fits are included in SnowScat, so you can get them as well for each different particle type. But if you remember, I already told you that we found some particles that are best fitting the scattering, and thanks to this approach, we can consistently model also their fall speed. So the question is, what happens if we modify ICON and the microphysical scheme of ICON, including this new mass, area, and fall speed parameterizations? And long story short, we did it. We've run some experiments, also some other sensitivity parameterization, but bottom line, we found that the new parameterization actually leads to a better matching between the simulated and the observed statistics of radar observations. There is a paper under discussion at the moment on ACP. So just to recap, I started with this pie plot. I showed you some snow particle models, which can give you a consistent microphysics and scattering properties for various particle types. Tools are publicly available. You can use them, and they're actually a lot of fun to use because modeling snow is such a beautiful task to do. We can use observation at multi-frequency and Doppler that can reveal microphysical properties of clouds, and the weather simulation are great for testing those parameterization and actually see what are the feedbacks of those parameterization to weather dynamics or to other important stuff such as rain rate. Of course, we ultimately want to get better and better forecasts. So with this, I conclude, and I ask you if you have any questions or comments. Thank you.
Well, thanks, Davide, for the interesting presentation. Not only for that, also for the scattering table that you are providing to the community. This is great. So, Paolo, you see some questions.
Thanks, Luca. So there is a question from Alessandro Battaglia in the chat, and the question is, Davide, in the simulation of DWRs, you have a convolution of effects from the scattering and the cloud modeling. So difficult to disentangle one from the other. Therefore, we cannot really conclude much on the scattering mode, can we? Any thoughts how we could more robustly directly validate snow scattering model?
That's a very interesting question. Yes, I agree. And Alessandro is perfectly right. There is a convolution of many different things that actually play at the same time. My point is that as we can include more and more observational constraint, we can also constrain our particle model. So at the moment, the best we can do is, at least for our observational data set, was to use multi-frequency and Doppler. If I can envision something about the future, I would say that the very next big step is to include some sort of polarimetric measurements, but that's already the most we can do, and it's already giving us a lot in terms of constrained particle properties. And of course, there is some uncertainty about that. If I can go back rapidly to the triple frequency plot. Here, or no? Yes, here. You see that there is quite a huge spread in the statistics of observation. And this depends on the continuously changing microphysical properties that cannot really be constrained into just one particle type. So there is still some uncertainty, but we are pretty confident that we are going into the right direction because we have consistent modeling of scattering and microphysical properties, and this is actually lead us to better matching of simulation and observations. That's my general answer to that, but I agree that it's complicated stuff and there is a lot of uncertainty around that.
Yeah, I don't know if Alessandro is satisfied from your reply, but I cannot see nothing on the chart, so I suppose that yeah.
Yeah, it's something we are working on. So I think several groups in Europe and across the ocean, actually, they are working on this. So it's a hot topic, and yes, it's quite difficult, yes, for sure. Yeah, I was just wondering, because at a certain point you mentioned, could we average all the scattering database, and you left that question unanswered somehow. So what should we do with all this scattering database? That's the fundamental final question.
Yes, thanks. So that I mentioned also it was a provocative opinion or answer to the question which particle to pick. My view on that is that we have more and more scattering databases, and we are going to have even more in the future. What we should do is to use them, trying to identify what we can learn from scattering and how scattering is connected to microphysics, or more specifically to particle type. So the answer might be even like there is too much uncertainty. We have too many different particle types that are actually leading to the same scattering properties. So that's like an unsolvable problem. It might be. I don't believe that's the correct. That's what is going to happen. But my answer is we should use them and be clear about which scattering properties are we using every time, and not just mentioning that, hey, I'm using scattering simulation, I should be great.
Okay, I think we can move on. I have the feeling, I bet that the scattering database of Davide is the best available in the world for some reason. I don't know. And I want to remind that we will see Alessandro in a talk in the afternoon session. So the next speaker is Alexis Berne. Is ready. Alexis Berne is from the École Polytechnique Fédérale de Lausanne, and is this APFL, let's say in short, will be organizing with Meteo Svizzera, let's say in Italian, the next IRAD 2022. After the missed IRAD 2020. So if you want to promote IRAD 2020, feel free to do that. The presentation will be again about snow, with example of snow in Antarctica. Again, most of the people, the community of Italian RadMet are focused on Italian weather, Mediterranean weather, but there is a larger science community working also in Antarctica, and some of them, some groups are working on precipitation and using this and using radars as well. So I'm glad to pass the floor to
Alexis.
Thank you, Luca, and thank you for advertising ERA 2022, which will be indeed in Switzerland. So I won't repeat that. So let me share my screen. Oops, sorry. Okay, and then presentation mode. I hope you can all see. So yes, microphysics of snowfall and radar. So it's actually Davide nicely introduced the topic. So I'll gain time in explaining some of the basics. Hopefully there will be also complementary or different aspects that I will touch upon. I would like to acknowledge the different people listed here who all contributed to what I'm going to present. Importance of snowfall. So yeah, again, Davide nicely introduced it. Just here, a slightly different perspective, maybe more oriented towards application and operational questions. So snowfall is significant, if not dominant, in total precipitation at high altitudes and latitude regions. It's crucial for various aspects that are critical for our society. So water resources, the Alps are the water tower of Europe. Snowfall may have direct impact on human activities, transportation, tourism. So yeah, snowfall is important, but monitoring and quantification of snowfall remains challenging. For the slightly more microphysical point of view and atmospheric point of view, again, Davide mentioned that. So we see here from these past studies that most of the raindrops originate in the ice phase over mid and high latitudes and over continents. And as was also mentioned, cold microphysics is not as well understood as warm microphysics. Talking about snowfall microphysical processes very quickly and very in a nutshell, what are the processes we are talking about here? So I will highlight three main processes. The first one is related to ice crystal and their formation and how they grow. So we start from nucleation, ice nucleating particle that grow by vapor deposition mostly. And this is bluish rectangle, and this is an illustration of this process of growth by vapor deposition. We have a secondary ice production, which is a slightly different process, which does not involve ice nucleating particle, but some kind of small ice pieces that are ejected by different mechanisms that can serve as ice germ. So that's secondary ice production. These are the schemes in green. Then later on, or lower down in the atmosphere, we have aggregation, when two ice crystals collide and stick together because of different reason, and remain together, forming a bigger particle. And we finally have riming, which is the collection of supercooled liquid water droplets that freeze instantly upon contact with an ice crystal. And riming is an important process because it converts very efficiently cloud water that does not precipitate to precipitation water. So these are the three main microphysical processes that we are interested in for snowfall. They're not the only ones, but the dominant ones, let's say. So we have seen in this very brief introduction the importance of snowfall and what are the main processes. So now in this talk I will cover the snowfall microphysics and radar, how we can derive information on those microphysical processes using radar measurements, weather radar measurements. I will make an illustration with a case study in Antarctica, as Luca explained, and finally some conclusions. What are the challenges in remote sensing of snowfall? Again, here I have to thank Davide because he nicely introduced the topic, and you see that we're very consistent. I also have mask images, but from the Alps, not from Utah this time, to illustrate the huge diversity of shapes, size, and types of ice crystal and snowflakes that we can find in snowfall. And so this variability, this variety is a source of uncertainty because, of course, when you shoot in the atmosphere, you don't exactly know what's up there. And as again nicely explained by Davide, their scattering properties are difficult to accurately predict and simulate.
So the question is how to get microphysical information from radar observation. And there, we'll start with polarimetry. So you're all familiar with the polarimetric radar. So we have in addition to reflectivity, we have polarimetric variables that are related to the non-sphericity of the particle, of the hydrometeors, basically. Let's consider, I hope you can see my pointer. We have here this kind of schematic profile of crystals and snowflakes and processes. So we start from the higher up in the cloud, where we form the ice crystals, mostly by vapor deposition. Then if the temperature and humidity conditions are adequate, we can have aggregation. These crystals are sticking together. Depending on the occurrence of liquid water, supercooled liquid water droplets, and other conditions, we may have secondary ice production, here illustrated by the Hallett-Mossop. So these ice splinters are ejected during the collision. So secondary ice production, and finally, if we have enough supercooled liquid water, we can go to the full riming of the particles, forming Graupel, so particles for which we cannot distinguish anymore the initial shape of the crystals. So we will use this typical profile to see the typical signatures in radar data. So if we are looking at polarimetric variables, and we will focus here mostly on ZH, so the reflectivity and the differential reflectivity, ZDR. If we start higher up, we have low reflectivity values and low ZDR, and then we have an increase and faster increase for ZDR, because we grow, these crystals tend to grow as very oblate particles. So we have a stronger increase in ZDR than in ZH. Yes, small particles, the concentration are usually not that big. So we have an increase of both ZH and ZDR in the upper part of the cloud. And then when we enter the aggregation zone, we have a stronger increase in ZH, because size, the aggregates are larger. So a strong response in reflectivity. And we start to have a decrease in differential reflectivity, because we have a decrease in overall density of these aggregates. So decrease in ZDR, and also the shape is more spherical for these aggregates than for the pristine crystals. So we have this decrease in ZDR, and we go on with it's a similar situation for riming. The signature of riming in differential reflectivity is slightly more complicated, because we have two competing effects: density, which is increasing, and therefore ZDR can increase, and the shape, because of the rime field of voids, tends to be more compact, more spherical, so it decreases ZDR. So overall, depending on the amount of riming and the stage at which we are, we may have ZDR slightly increasing, but overall, it's rather a decrease in ZDR that we have. So this is a typical profile, polarimetric profiles that we have with the signature of these different processes. The limitations or pitfall or caveat that we have to keep in mind is that beam elevation must be below 45 degrees if you want to use ZDR. If you are at a higher elevation, then you somehow lose the ZDR because of the orientation of the particle. And of course, using ZH, calibration must be reliable. Second possible approach is using the Doppler information. So this time, we suppose that we have a radar with the Doppler capabilities, and we can store the Doppler spectrum. That's what is illustrated here. And because the terminal fall velocity of the particle depends on size, shape, density, and so on, there is information, there is a microphysical information to be extracted from the Doppler spectrum. And what you have here is exactly that. So the vertical is the altitude, the range gate, and the color coded here we have this Doppler power spectrum. So for each range gate, we have, according to certain velocity beams, the amount of power that is reflected back to the radar. So from that, we can extract the classical Doppler variables, the mean Doppler velocity, which would be the line here corresponding to the mean of this color-coded spectrum. The spectral width, which is the standard deviation of the spectrum, so it quantifies the width of this spectra here. And finally, as illustrated here, we have the spectral variable, here the spectral reflectivity, and if you have a polarimetric radar, you could also have a spectral polarimetric variable. And so the typical evolution is that we start up higher up in the cloud with low reflectivity, rather limited fall velocities. When aggregation is kicking in, we see a strong increase in fall velocity related to the size, and also a strong increase in the reflectivity, more reddish colors. And I will come back later on what's happening here. It's more complicated. So if we again use our schematic here, in terms of signatures, we would have, for the upper part where deposition is dominant, we would have rather low velocities and spectral width, velocities typically below 1 meter per second. When we arrive where we have rhyming and aggregation, we will have an increase in the velocity and in the spectral width. If we have secondarized production here, we could expect bimodality, so a second mode in the spectra that is related to this new population of particles that are generated at this altitude, and this is figured by this dotted line here in red. And importantly, turbulence has a strong effect on broadening the spectra. So the limitations or the caveat here are the possible contamination by vertical wind, because what I said before about the terminal fall velocity, of course, in the atmosphere, you combine this terminal fall velocity and the vertical wind, which can be difficult to get exactly, and the mixing by turbulence, which may completely blur these typical signatures that we can encounter. And actually, if I just come back here, that's exactly what's happening here. We enter a turbulent layer, we see a clear broadening of the spectra and even updraft. That's why the mean velocity is decreasing despite the aggregation taking place. Third approach that was already explained by Davide, the multi-frequency. So, well, you all know the different scattering regimes, and the idea is to combine two or more frequencies to use the fact that when we're dealing with small particles, all radar signals at all frequencies will be mostly in the Rayleigh regime, so the dual frequency ratio will be close to 1. While for larger particles, the lower frequency will still be in the Rayleigh regime, while the higher one will be in the Mie oscillations, and therefore the dual frequency ratio will start to be quite bigger. And we can also do spectral dual frequency ratio, so we look at the DFR per velocity class, so to speak. So again, if we come back to our schematic, what's happening roughly in the deposition phase, or in the region where the deposition is dominant, we have the DFR which is close to 1, and it strongly increases when we have an increase in size due to in size or density, so due to aggregation and rhyming. And again, as was mentioned by Davide, to better distinguish between aggregation and rhyming, a triple frequency has been shown to be a promising approach to disentangle which process is dominant in which part of the atmosphere. The limitations here are the beam matching, because of course you need to have the population of drops that are sampled to be as close as possible, and if there's too much difference in the radar volumes, you may simply not sample the same thing. And again, accurate calibration, so because you need to compare reflectivities at different frequencies. So I quickly reviewed how we can derive information about microphysical processes from different radar approaches. So now, just as an illustration, I would like to focus on snowfall across scales and look at links between atmospheric dynamics and microphysics by combining multi-frequency dual pole radar observation and NWP, so numerical weather prediction model simulations. And we have all these interactions between processes at different scales that basically govern the snowfall we see at a given place. So for this illustration, we will focus on a case that happened on the Antarctic coast during the plateau campaign. we selected this particular event because they were all synoptic ingredients to have intense precipitation. But it turned out that at the station at Davis, where we were, there were barely any snowflake falling at the ground. So we were wondering what was happening, and again, what was happening at different scales to explain what we saw locally. So very quickly, what about this campaign? It was at the Davis station on the coast of the Price Bay. So on the map here, this is Davis. So this is the peninsula. So South America is here, Africa is there, and Australia is somewhere there. Just to give you an idea. So Davis is here on this Westfold Hill area, very flat, close to the coast. But note that it's downhill of a big ice ridge line that has some impact. We'll see. In terms of instruments, we will use the data from this scanning X-band polarimetric radar here and this vertically profiling W-band Doppler radar. So 2 frequencies and a polarimetric radar. Quickly, I would like to introduce the synoptic situation, especially at the beginning of the event. There are 3 phases. I won't have the time to go through all those 3 phases, so we'll focus on the first one. So Davis is here, this is Price Bay, and this is the continent. So north is up, south is down. We have a cutoff low here to the northwest of Davis that result in a northeasterly wind field in the area of Davis here. If we add the potential temperature, we clearly see a warm front associated to this cutoff. And we also see a cold air pool over Price Bay here. And this cold air pool and the warm front that results in a barrier wind here. So we have the deflection of the wind, synoptic wind, due to this cold air pool here. And if we finally add the information about moisture transport by the integrated water vapor, we clearly see that there is a strong meridional transport, so from the north to the south. And that's why I mentioned that we were expecting, we had all the ingredients for intense precipitation because we have a strong meridional moisture transport. What do we see locally over Davis with the different radars? So on this figure, you have along the time axis in the y-axis and the altitude on the y-axis. We have first the reflectivity measured at 95 gigahertz. Okay, we have the Doppler velocity, the mean Doppler velocity measured by the radar. And here we have the more microphysical information related to hydrometeor classification. So the panel C is only relying on X-band polarimetric data. And so just to help you understanding that, the greenish colors means that we have a dominance of crystal. The bluish colors means the dominance of Rhine particle, and the reddish dominance of aggregates. Ooh, I'm late, so I need to move on. And here it's a dual frequency ratio between X-band and W-band. So what we see is that if we focus in with the 3 phases, 1, 2, 3 here, we see that despite having strong reflectivity, so intense snowfall higher up, we have almost nothing reaching the ground. So total sublimation, especially during phase 1 and 2. 1 and 3, sorry. We see, looking at the Doppler information, a lot of turbulence in the lower layers, so this alternation of red and blue things. And 2 main zones for aggregation, these orange reddish areas that correspond to intense aggregation. And what is nice is that these 2 plots are not completely independent because X-band reflectivity is used in both, but they are very, very consistent despite being based on a very different approach about identifying the processes. So again, we'll focus on this first phase. I will move fast. If we look at the area, what's happening around the station of Davis, which is here, we see a very strong updraft, and this reddish color. So this map here is the vertical velocity at 800 hectopascal, simulated by WRF. Okay, so we see a very strong updraft. that if we add the temperature, we see that the warm front is somewhere here. So we have lifting associated with the front, but not to the, that does not explain the very intense updraft we have here. We can also see that we have some kind of waves trapped below this altitude here, where we have increased static stability. And if we look at especially here, this vertical cross-section along this brown segment here, we have a clear Föhn effect. We have the like downwind slope that warm adiabatically, and then we have a hydraulic jump at the foot of the ice ridge, and that explains this huge updraft here. And if we add the information about relative humidity, we see that we have very dry air associated with this Föhn wind, and that's why we have complete sublimation of precipitation over Davis, because we are in the area where we have this very dry air tongue extended due to the Föhn effect. If we look at the spectrogram from the X-band parametric radar, we see a very consistent thing. So growth by deposition, aggregation starts, strong increase, explaining the strong reflectivity we see, and then suddenly we enter this area where we have a lot of turbulence, updraft, and we see that, and complete sublimation here. These remaining echoes are just ground echoes here. So there's a very strong agreement between the radar and the model for this case. So we can put everything together in a conceptual model of what's happening during this event. So we have the low, we have the warm front, the moisture flux, and we have this, due to the interaction between the synoptic wind and the ice ridge, we have this Föhn wind and orographic waves that generate this dry air sublimating completely the precipitation and generating also a lot of turbulence that promote and enhance aggregation higher up that we could see with the radar. So to summarize, snowfall and ice microphysics is very important. We have very quickly seen that we can use dual pole, Doppler, or multi-frequency signatures to characterize, to derive information about microphysics in snowfall. It's not always super clear, and there are ambiguities. And I briefly presented a case study for which radar observations made possible to identify dominant processes in relation to larger scale dynamics. Very quickly, a few perspectives. Multi-frequency dual polarization spectral radar observation are probably what can provide the maximum microphysical understanding. And extracting such information from radar observation is very useful for evaluating models, and also to complement the information from models for process understanding, as I illustrated in this case study. And finally, many operational radar are polarimetric. So in my view, there is a large potential in operational data and archives to go and dig out more information about microphysics in snowfall. And with this, and being a bit late, I thank you for your attention and will be happy to take any question.
Okay, thanks, Alexis. And Paolo, what about questions?
There is one question from Alessandro, but since Alessandro is present, if you want to ask directly.
Yes. Any clue if you had some super cool liquid layers during the event you were describing?
So we had a LiDAR. I didn't present it, which was useful to detect. Of course, the issue is that when you have such intense precipitation higher up, the LiDAR signal is completely blind. We didn't have a radiometer, so there was some, but it was not rhyming was not super dominant in this event. This remained a bit speculative because, of course, we didn't have all the instrumental means to make sure that the conceptual model we propose now is fully correct. But as soon as you have strong updraft like that and a lot of turbulence, you can expect to generate some supercool liquid water. The exact extent is difficult to quantify.
Okay, thank you.
if there are no questions, I have a question, and I totally agree with your last point. So that we have to look better at the dual polarization data that we have collected so far in operational radar and so on. But it's clear that to understand the snow process, precipitation formation processes, we have to rely to diversity of information. So the question is, which is the best and affordable combination of instrument that you at the moment can suggest accordingly? I know this is there is let's say the theoretical gain you can have, and there's also where you plan to deploy your instruments. Yeah. Because of course, and Antarctica is a bit extreme, but even simply being in the Alps in winter, you may have the most fantastic, super fancy radar combination, but if the thing cannot work in tough conditions, then you basically will have nothing. So I think there's also this question of where the instruments will be deployed and in which condition, and that is a strong constraint on what makes sense to be deployed in these conditions. But I would say I like very much this combination of polarimetry, something scanning, because then you have this horizontal information, but in combination with maybe less fancy vertically profiling radar, but still you can arrange that every few minutes you collect like collocated vertical profiles for which you can use spectral and dual frequency information, for instance. So yeah, my suggestion would go in that direction, but probably there is a personal bias in that answer. But I agree with you, and also agree on the fact that practical aspects count a lot. Should not be underestimated. Yes. So thanks I thank Alexis for this great presentation, and pass the ball to Pier Paolo for the last talk of this session. Of course.
Thanks, Luca. So I'm glad to give the screen to Guido that will speak about quantitative precipitation, so we can move from snow to rainfall. And so Gui, the screen is yours.
Thank you very much. I hope you can hear me. I share my screen. Yeah. Can you see the presentation? Yeah. Can you see the mouse?
No, but we can see not the presentation, more about the other one. You have to screen.
Maybe you are not in full screen mode, maybe.
Here, can you see it or not? I have to redo.
We see this. We see the actual slide and the next one.
Guy, va dans paramètres d'affichage et tu inverses les écrans. En haut. Au milieu. Paramètres d'affichage.
Et alors, paramètres d'affichage.
Là, tu dois pouvoir...
Maybe I stop and I redo. Écran partagé. Here, can you see it?
Okay, much better.
Better? So hello everybody. Thank you for inviting me to give this talk. My name is Guy Delrieux. I'm from Grenoble in France. I will present this topic about quantitative precipitation estimation which is not our most recent work, but it is something that it is a long-term project, and I think it is important from time to time to revisit and to re-explain the kind of objectives we have. I acknowledge the contribution of my co-authors. Brice Boudvillain is the main of them. He's now the responsible of the observatory that we are used to manage together. And I acknowledge the contribution of several early stage researchers that were involved during the years in this project. So the idea, the idea is to provide a hydrologist with long-term rainfall reanalysis at spatial and temporal scale that are relevant with respect to the hydrological dynamics of a given area. So typically we want to consider long-term means 20 years, greater than 20 years, with the regional scale, fine resolution of, let's say, 1 square kilometers and one hour, it can be better. And when we have this in mind, we are convinced that physically based radar data processing is required to get some reliable quantitative precipitation estimates. We may wonder if it is sufficient, and in my view, it is still not sufficient. We have to consider also other sources of quantitative information. And in this respect, raingauge network, of course, have a strong potential. When we accept the merging idea, we have to think about the merging techniques that we should implement. And when we do that, we have to wonder if, finally, there is an added value of the merging with respect to the performance of the two observation systems that we consider separately. And of course, hydrologists and everybody in physics need to have some idea of the errors that we have on our estimations. And this is, of course, the problem, the error model on quantitative precipitation estimate. We have in mind some hydrometeorological applications. For instance, the quantification of errors in distributed hydrological modeling. Also, the quantification of heavy precipitation, extreme precipitation, and the detection of trends. And also, we can use this data to assess numerical weather prediction forecasts or satellite rain products. Within our observation activities, we have a focus on a region in France, in the southeast of France, which is a Cévennes region, which is prone to heavy precipitation and flash flooding, and which is consequently, which benefit of quite a dense rainfall observation system made of 4 radars from Météo France network. 2 of them are S-band radar in Nîmes and Bolène, and 2 of them are C-band radar in these 2 locations. We're considering this window, of which size is about 32,000 square kilometers, and there we have, in addition to the radar, 200 hourly rain gauges and 116 daily rain gauges. And within the long observation period of the IMEX project, we have complemented this observation with radars, but also with distrometers, but I will not speak of that today. Regarding the merging technique, we promote the use of a geostatistical technique in the family of those presented by Ioannis Sideris before. And the method we promote is a kriging with external drift. To explain this briefly to the young generation, not to the radar people, here the x-axis is the dimensional space Earth of the Earth. This is a rain rate on the y-axis. The blue curve features the radar quantitative precipitation estimate. The red points feature the observation, rain gauge observation that we have in space, and the red light feature the interpolation that we can perform on this data using ordinary kriging, and which produces generally a more quite a smooth precipitation field. The CAD technique works, in fact, in two steps. The first step is to derive the drift. The drift is obtained by a linear transformation of the raw radar data based on the correlation and simple correlation analysis between the points that we have where we have rain gauge and radar observation. So this first step allows to remove the bias which is eventually present in the radar data. And the second step is to make a kriging of the residuals between the drift and the rain gauge data, which allows to produce this purple curve displayed in this graph. So this is an example for an hourly rainfield that we have in the Cévennes region. With you can see that the consistency between the kriging, the rain gauge estimate, and the radar estimates is quite good in that case. This is the drift, and the drift is well, we don't have a big problem of calibration for this stem, so it's quite similar to the radar. And the CAD product finally will preserve the fine scale structure of the radar and make some adjustment where the rain gauge network has seen some values that are different from the radar, corrected radar. So this is a good case. I present here the case of a very poor correlation between the radar and the rain gauge estimates. In that case, the correlation between the spatial polarization is low, and so the A coefficient of the drift will be close to zero, and so the drift will be essentially flat. And when we do that, the CAD estimate will rely essentially on the rain gauge data. This is illustrated here with a very terrible case of a problem. It was in January, in winter. We had here a terrible problem with the bright band contamination of the radar data. And so as you can see, the CAD drift is essentially flat, and the CAD estimate is close to the ordinary kriging of the rain gauge. So the method is able to automatically discard, so to speak, the radar data that should be considered as poor. Another example is here with, again, this is a convective case in summer. And you can see that there is a quite good consistency of the rain gauge and radar data, except that the rain gauge totally missed this convective cell, which is present in the south part of the image. The CAD, since the spatial correlation is quite good, the CAD is able to keep this information. So this is, so to speak, a smart technique, and I think it is one of the best merging technique that we can think of. Regarding the idea of assessing the benefit of the merging with respect to the two observation system considered separately, I present here the results of 16 years of reanalysis in cross-validation. We have here about 300 rain events. The time step is 1 hour. Two criteria: the bias between the ratio of the estimated to the observed data, and here the square of the correlation coefficient spatial for each rain event. In gray, the ordinary kriging performance, in dotted gray, the radar performance, and in black, the merging. And well, there are maybe two major results that we can take from this image. First is that in terms of correlation, the merging is systematically better than the two other estimates. And in terms of bias, all these methods, tends to be unbiased, but you can see that there is a break point in our time series, which corresponds to the implementation in 2007 of a new QPE system, which proved to be much efficient, especially in terms of bias. Another, a more detailed view of the result is by separating what we call the Cévennes rain events, which are long-lasting events with moderate intensity that give rise to shallow convection over the mountainous part of the region. And as you can see in that case, we have a cumulative rainfall of about 500 millimeters in 2 days. We also make a class of events that belong to, let's say, localized convection cases. And it is interesting to look at the square of the correlation coefficient for these two types of event, 50 cases and 40 cases here. And as you can see, for the Cévennes events, the radar performance is really quite low. It is improving over time. And you can see that, in that case, the rain-gauge network makes better work, but you can see that there is a significant added value of the margin, especially in the most recent cases. This is the contrary for the localized convection. The rain-gauge network is not really able to detect such fine-scale systems. The radar is better, and there is, again, in some cases, benefit, an added value of the merging compared to the two systems. The error model. So I go quickly on that, but the idea was to derive a geostatistical model, and the idea is to be able to associate to each rain rate estimate over the original radar grid, or over what we call hydrological meshes, which correspond to subdivision of the watersheds of interest. Associated to that, an estimation of the error, the standard deviation of the error. And we devise a very quite simple but efficient model, which is say that the standard deviation is a bilinear function of the rain rate and the creating a standard deviation estimation standard deviation, which is the quantity that the Kriging system minimizes in this optimization. And so this coefficient, well, I skip the details, but we use a method that was published, an original method that was published some years ago to estimate this coefficient. If we look at this error model in terms of the ratio of the standard deviation to the rain rate values, the scaled standard deviation of error, for a range of time scales and a range of space scale, we see that the Kriging with a certain decade method overpasses the simple rain gauge estimation. This is true at all scales, but maybe more at the shortest one. And this is even more true for the localized convection. and not because the decade is improving so much, more but because the rain gauge network has a poor performance for this localized convection case. So this is published. We also to provide hydrologists with a rainfall space-time series. We develop a rainfall generator, which is while similar to a Swiss generator that was published some years ago by Michael Swiss and German. The idea is to take into account the space and time structure of the error to generate a time series of precipitation, and you can see here the generation of cumulative precipitation over a watershed of 50 square kilometers and over a watershed with a bigger size, of course, with reduced dispersion of the values. These ensembles can be used and were used in distributed hydrological modeling. This is an example for the Ardèche river that we have which is one of the sensitive watershed in our region of interest. And this work led to a study within a PhD thesis of the relative importance of the precipitation uncertainties with respect to the model parametric uncertainties. So it is an example of the kind of hydrological use that we can do with these simulations. Another application is on the quantification of intense or extreme rainfall, and it is about the idea of modeling the relationship between intensity, the duration, the area, and the frequency of precipitation. So this is a brief illustration of this kind of type of work. And we have to know that you have to know that this type of model is really used by hydrologists to design sewer systems or this kind of infrastructure. So it is quite important, and the aerial dimension of this model is often quite poor because this model are often derived from rain gauge control values, and there is a lot of improvement to bring into this model. So just to illustrate, this is the 95% quantile of the CAD max rain rates over a period of 8 years in our region, and you can clearly see that we have two domains, two regions in our pilot site. In this area where the weather and the rainfall is mostly influenced by oceanic weather, while clearly in the Cévennes area, in the plain part, the Mediterranean influence is really present. So for this region, we perform a regional analysis of which consists in detecting a maximum value for each event for different duration areas. We fit some distribution and we make some modeling. And I just want to show you that when we consider the radar data in this rain rate return period plots for different size of the domain that we consider, we have a much higher rain rate values for the CAD than for the rain gauge alone, and this has, of course, big implication on this type of model. Of course, the departure between the scales between the two system observation is reduced when we increase the time step. Trends. This is of course not to the topic which is up to date and important. We have some way in our group. We have some researchers that prove that there is some trends for part of this region, but this is at the daily time step using rain gauge data, and I think that we will have some proposition to make with our reanalysis. Conclusions. Long-term high-quality radar rain gauge reanalysis, in my view, are really needed, both for the science and engineering, and also for climatological studies. We have shown in our work that there is an added value of the merging, and there is an added value of the radar information for the smallest space-time scales. You have to be aware that this is quite a painful task to establish those reanalysis. It is quite takes time and energy. The critical point is the quality control of the rain gauge data and the radar data. of course, we acknowledge, we welcome any improvement in the radar QP algorithms, and our procedure is a way also to monitor this kind of progress. And it could be people ask for more physically based radar error models. This is something that we could think about. I have other story, but I will stop here. Not to take too much time, because I think the audience might be hungry at that time.
Okay, thank you, Guy. Thank you also for accepting to illustrate a well-consolidated technique that is always good to make other people aware of your well-consolidated research. So far there are two questions. First, Ioannis, and you can take the.
Okay, thank you so much, Guy. I really appreciate this talk. As you know, I have two questions. The one is about the cross-validation. You showed the multi-year. I noticed that the KED has a preference to give negative bias. So it is not. I don't care about the fluctuations, but it seems, if I understood well, that it's not centered around the zero bias. Is there a reason for that? This is the first question. And the second one is if you have any system regarding the representativeness of rain gauges, because sometimes in extreme events, convective cases during the summer, a low representativeness rain gauge may affect very negatively the semi-variogram. And this depends on what weather the radar shows above the rain gauge. Of course, you have many rain gauges that you may be safe, but just your comment on that.
Yeah, I agree with you. But the computation is made using the data available, and so I try to give let's say a view of to explain the Kriging, the CAD functioning to people who don't know. But of course, all this is done automatically using the variograms of the residuals and all these things. So I think the problems of representativity that we may have is managed by the computation of the variograms. Regarding the first question about the bias, yes. Well, all these methods of the Kriging techniques are, as you know, use unbiased estimators, but maybe for time to time and in cross-validation mode it's a bit strange, but if we consider other information, we have used also for the validation the daily raingauge that were not used for the Kriging implementation. So well, maybe I have to look more precisely to your question, but I don't think that it is a big trend to have negatively biased CAD estimates.
It is a little systematic. I don't care about the fluctuations, but it seems that it is always below zero. But you have a look at this, okay? Thank you.
Thank you.
Thank you, Guy.
Thank you. And now Remko can ask a question.
Hey, Guy, good to see you. Hi, greetings from the Netherlands. Guy, thank you very much for your nice review presentation, and congratulations with a long-term effort in the Cévennes-Vivarais region in terms of radar QPE. Very valuable contributions to the science on radar rainfall estimation. A question that I have, and that I probably know the answer of, but that is probably also important for the audience here. When you talk about radar gauge merging, your example of Kriging with external drift. The radar product that enters that merging procedure, is that a radar product that has already been, let's say, corrected for a number of potential error sources when it comes to rainfall estimation? Thinking of, attenuation, hydrologic visibility, VPR, what else? Could you perhaps comment on that?
Yeah, I forgot to mention it, but of course, this is the radar product that we use is the product disseminated by Météo France in real time. So it is a mosaic, the French mosaic, and of course corrected as far as possible for the VPR effect, for any, and there is some kind of adjustment with the raingauge, but it is made in a very let's say uniform space, and so we feel, of course, we have to ingest in this kind of merging the most elaborated radar data, and we don't want to. Although I have shown that we are the CAD is able to discard very, very bad data like this bright band contamination, I think we should not do that, and we should try to use the best radar information we have before the merging.
So basically, what you're saying is that Kriging with external drift or any other sophisticated merging technique is really the very last step in a whole chain of, let's say, careful radar data processing techniques exactly. in the QPE endeavor.
Yeah, and we have to convince hydrologists, and I think the procedure that we propose to continuously monitor the performance of the three system of observation, the radar, the raingauge, and the merging is essential to convince people that we and the error models that they could use radar data in hydrology.
Great, thank you very much. Keep up the good work.
Okay, thanks. I would like to thank all the speakers. By the way, I would like to support the effort of Guy to convince people to use radar and raingauge at their best. So we are at the end of this session with 15 minutes delay. This is almost Italian standard. I thank also the co-chair Pier Paolo Alberoni, who is not here, and I see. I think Andrea can take the screen and conclude the morning sessions.
Thank you, Luca. Thank you also to Pier Paolo for co-chairing this session. And now it's time to have a lunch break. But before, I would like to mention that in the afternoon the YouTube link will change. So you have to connect with another link that you can find in the website of the conference or in the channel of YouTube channel of LaMMA, Consortium LaMMA. Some numbers of some statistics of the connection of this morning. On Zoom we had more than 60 connections, and on YouTube we had more than 180 connections. So that it was a success for us. Now it's time to go in lunch break, and we will restart the session on 2:30 in the afternoon. So thank you very much, and see you later.